Zarate sir, and Vyas sir, and Dr. Dattatreya Latte. I welcome you all to this to this international workshop on recent trends in nanoscience and nanotechnology, organized by Center for Nanoscience and Nanotechnology, Amity University, Maharashtra, Mumbai. A very warm welcome to one and all. So, in today's session, we are going to learn about the various aspects of nanoscience and nanotechnology. And I hope that you all will have a flavor of all the branches that nanoscience deals with. We have got together experts in different fields of nanoscience and nanotechnology to give you an idea about the vast expanse of this subject. So I hope today's session is enlightening to you all. And with that, I request Dr. Latte sir to kindly give the opening message.
Good morning, everyone. I am Dr. Dattatreya Latte, convener International Workshop on Recent Trends in Functional Nanomaterials for Technological Application. The world is full of diamonds and gems, and we are having some of them here today to build this event. The ability of science and technology to improve human life is known to us. Technology has ever more productive. I'm not opposite of the technology. We are Amity University Center for Nanoscience and Technology. We are currently in an inaugural function of this center based on nano research. With this note, I would like to give my heartiest welcome and brief introduction of our guests, mentors, and visionary leaders of Amity. It is my honor to welcome you all on this day, where we will be beginning a new journey in the field of functional nanomaterials, recent trends, updates, and achievements. Today, we have with us Professor Dr. W. Selvamurthy sir, President, Amity Science, Technology and Innovation Foundation, Director General of Amity Directorate of Science and Innovation, Chair Professor of Life Sciences, Chancellor, Amity University, Chhattisgarh. He has published more than 15 books, more than 200 research papers. Professor Selvamurthy sir is distinguished scientist and serves as a Chief Controller, Research and Development at DRDO. He is a postgraduate in human psychology from Christian Medical College, Vellore, in 1972, PhD from University of Delhi, studied reception of several doctorate of science degrees from various institutes. We are with us Professor Dr. Amity University, Mumbai. Dr. A.W. Santosh Kumar is currently a Vice Chancellor, PhD from All India Institute of Medical Sciences in New Delhi in 1999. He holds 19 patents and published more than 200 research articles in recognized international journals. He has completed several funded projects in India as well as USA, and he is leading our institution. Held positions of Vice Chancellor in universities with A+ National Assessment and Accreditation Grade. And currently, Dr. A.W. Santosh Kumar sir is leading Amity University, Mumbai, in exactly a new horizon world, and he is bringing new research and technology in the Amity University, Mumbai. We have with us Dr. Hira Vyas, Honorable Registrar, Amity University, Maharashtra, Mumbai. Dr. Hira Vyas has MBA alumni of the Southern New Hemisphere University, Manchester, United States. Sir is also fellow member of CMA Institute and is awarded PhD from Nagpur University in Commerce Faculty of Business Management. He is also qualified in financial modeling from Bombay Stock Exchange. He has a rich experience of working in corporate and education sector over 30 years. We have with us Dr. Srikant Charate. He has completed his PhD from IIT Bombay. Sir is Professor and Director of Amity School of Engineering and Technology, also Director and Coordinator for Amity IPVCCL. Sir has very vast research and teaching experience earlier, and he is leading this Amity School of Engineering and Technology. So we are currently working and living in this new normal where most of us have no choice but to work from home, office, and manage remote teams. Working hard is always working smarter is even better. In the pre-workshop program, yesterday we have received more than 7 posters which were presented online. Participants were joined India, Pakistan, Brazil, Mexico, China, France, UK, and presented their research work. I am looking forward to an impressive program today and confident that all participants will find.
Dr. Latte, you are once again on mute.
Dr. Reddy, over to you. Yes, sir. Hello, sir.
Sir, we can hear you now.
Yeah, okay. Over to you.
Hello. Hello.
Hello.
Sir. Hello, sir.
Yes, madam, we can hear you. Yes.
Okay, sir. So next with the kind permission from Dr. Latte, sir, next we have an address by Honorable Professor Selvamurthy, sir, Honorable President, MIT Science and Technology and Innovation Foundation, Director General, MIT Directorate of Science and Innovation, Chancellor, MIT University, Chhattisgarh.
Thank you. Thank you. Very good morning to each and every one of the delegates who have joined us at this very important the conference, which is being organized by our Amity University, Mumbai, in Maharashtra of India. So I welcome all the delegates on behalf of Founder President, Dr. Ashok K. Chauhan, the Chancellors, Dr. Atul Chauhan, Dr. Asim Chauhan, and also on behalf of all members of Amity fraternity. It gives me immense pleasure to welcome every one of you to this very important conference on functional nanomaterials for technological applications. Let me particularly welcome Dr. P.K. Tripathi from USA, Professor Shinde, Germany, and Dr. Karevar, the Netherlands, Dr. Rati, South Korea, Dr. Pawar, and Dr. Basu, and many more, Dr. Bodkar, and I won't be able to take all the names of very distinguished scientists who have made a mark in this field of nanomaterials and its characterization, synthesis, characterization, application, functionalization. So I welcome each and every one of you. My deep appreciation to the Vice Chancellor, Dr. Santosh Kumar, who has been Vice Chancellor responsibility in many other institutions before joining Amity. Now he is giving an excellent leadership at Amity University, Mumbai. Dr. Santosh, congratulations to you for this wonderful conference which you have initiated. And Dr. Dattatreya Latte, the convener, and Dr. Arif Shaikh, the co-convener, my appreciation to you that you thought of a very important topic, the nanomaterial applications for technology development. And I must also appreciate Dr. Shrikant Charate, the Dean of Science and Technology at Amity University, Mumbai. And I'm so happy I visited this university, our Amity University, Mumbai, a month ago. I could see the vibrance in terms of research, innovation, academics coming out from this young university of Amity Group and under the leadership of Dr. Santosh Kumar. So my deep appreciation to you on behalf of Founder President and Chancellor and the President, Dr. Asim Chauhan. I also like to share a few thoughts that this nanomaterial, the Founder President, Dr. Chauhan, started a separate institute, Amity Institute of Nanotechnology, way ahead, about 15 years ago in India. Perhaps this is the only separate institute in nanotechnology, which has churned out many doctoral students as well as the master students, undergraduate students in nanotechnology, and there are there. Founder is really a visionary who can start 15 years ago in Amity Institute of Nanotechnology. Our citation to Ashok Chauhan, this very thoughtful initiative which he has taken 15 years ago. when I look at now the application of nanomaterials, I find almost it is omnipresent. Everywhere you can find an application. When you look at agriculture, nano agriculture is really the precision agriculture. Nano agriculture is going to be the future with the land availability going.
I think Selvamurthy sir is traveling, so let us wait for two seconds. Automatically we'll get hooked up back.
Okay, sir.
Sorry, my connection got disconnected. Can you hear?
Yeah, now we can hear, sir. We are waiting for you.
Okay. Yeah. Thank you. So nano agriculture is the future, and a lot of effort, a focused mission mode program is on in the Ministry of Agriculture, where we are looking at fertilizers, pesticides to minimize its application so that the environmental hazard all this produces is also minimized. So we are looking at nano agriculture using polymer encapsulation of fertilizers, pesticides. And we are also looking at biofortification because many of our soil are deficient in zinc. So can we do the nano encapsulation of the zinc and then apply it on transfoliage, just root application, transfoliage. So this is yet another effort which is happening in Amity. And in Amity, microbial technology is being used to provide the abiotic stress tolerance against the cold, heat, low water availability, salinity of the soil, alkalinity of the soil. So in which we are producing Piriforma spora indica, which is a root endophyte. So when you apply titanium dioxide to the stress. There is also another effort in nanomedicine. We are looking at drug encapsulation, drug targeting using nanomaterial. I'll give an example which Amity is doing. We are in cancer. We are attacking the cancer stem cell, which is responsible for the recurrence of the disease, the initial carcinogenesis, and after the surgical removal, chemotherapy, it recurs for the simple reason that the cancer stem cell is still there. So this is yet another effort on drug encapsulation. Then we are also looking at the drug delivery for the diabetes, sustained release, and also nanomedicine. And we can also use it for the nano defense race.
Sir, Selvamurthy sir is not in the meeting now.
We'll wait for 2 minutes then.
Yes, sir.
You can proceed further. Dr. Selvamurthy will join in between. Dr. Selvamurthy will join in between. You can proceed further. Just leaving him, proceed further.
Okay, sir. Okay, sir. So that was Dr. Selvamurthy sir for us. Next, I request Professor Dr. Shrikant Sarate sir, Dean Academics, Amity University, Maharashtra, Professor and Director, Amity School of Engineering and Technology, Amity Institute of Technology, Director and Coordinator, IQAC, Amity University, Maharashtra. Sir, please enlighten us with.
Thank you, Dr. Riddhi. Am I audible? Connection is okay? I think
Yes,
today
sir.
we are facing a lot of issues with connectivity.
Yes,
Thank you very much and good morning to everyone. Honorable Chancellor of Amity University, Chhattisgarh, and our mentor, Dr. Selvamurthy sir. Honorable Vice Chancellor, Amity University, Mumbai, Dr. Santosh Kumar sir. Dr. Vyas sir, Registrar of Amity University, Mumbai. Dr. Latte, Dr. Sheikh, we were the conveners of this workshop, Dr. Iddi and my fellow colleague. Dr. Selamurthy sir has already given insight of this particular workshop and how the nanotechnology, nanomaterials are important in all the applications, including agriculture. Here I would like to say a few points that this international workshop in recent trends in functional nanomaterials for technological applications organized by this Center of Nanoscience and Nanotechnology, Amity School of Engineering and Technology, Amity University, Mumbai. Dr. Latte and Dr. Arif, they came with this novel idea to organize this particular workshop. And at the outset, I would like to congratulate both of them and entire team of Nanoscience and Nano Center. Nano Center. The nanotechnology is an interdisciplinary subject, as all of we know, which have contributed in various science and technological sectors and in industries. I think this workshop will cover up some cutting edge research based on transistor sensors and synthesis and applications of various novel materials. The nanotechnology is a futuristic subject which is growing very fast from a last decade. We are using this nanotechnology in our day-to-day life. As an example, like mobile phones, the Intel chip contains billion of transistors. Memory devices are increasing its storage capacity with reducing size, and batteries also made up with nanomaterials. With such an amazing technology, one can expect many solutions to bottleneck technology issues. The applications, as Shalom Professor also narrated few applications at food packaging, processing, and agriculture. This is very important sector which is coming up with use of nanometals and nanotechnology. Renewable energy is already using nanomaterials and nanotechnology, biomedical and healthcare, construction materials. So nowadays, I see there are so many papers, so many technological innovations which are happening in the field of construction material because we need to reduce the cost. The cost of construction is very high, and we need to reduce so as the life of the structures. Electronics and energy storages, environmental remediations. These are few applications of nanomaterials. I wish the organizers very best and all the participants very best to gain the knowledge within these 2 days. Thank you very much, Dr. Indi, for giving me this opportunity, and Dr. Light and Dr. Arif for organizing this particular workshop. Thank you very much.
Thank you, Zarate sir. Next, we have an address by Dr. Vyas sir, Registrar, Amity University, Mumbai.
Thank you, Riddhi ma'am. Hope I'm audible.
Yes, sir. Yes, sir, you are.
Respected Honorable President ASTIF, Dr. Selamurthy sir, respected Honorable Vice Chancellor, Amity University, Maharashtra, Dr. A.W. Santosh Kumar sir, Dean Academics, Dr. Shrikant Charate, Head Center of Nano Science and Technology, and Convener, Dr. Dattatreya Latte, Co-Convener, Dr. Arif Sheikh, distinguished experts from University of Mumbai, prominent speakers from international universities, and participants. A warm good morning to all. I welcome all to the international workshop on recent trends in functional nanomaterial and technological applications organized on virtual mode by the Center of Nanoscience and Technology, Amity University, Maharashtra. I take this opportunity to personally congratulate Dr. Dattatreya Latte and Dr. Arif Sheikh for organizing the 2-day international workshop. In his opening remark, Dr. Latte and our mentor, Selamurthy sir, has already given good insight about the topics that would be covered in this 2 days workshop. I'm sure all the participants must be eager to hear from the experts. I'm confident that all the participants would be highly enriched with the knowledge disseminated through the proceedings of the workshop. I once again welcome you all to the 2-day international workshop, and I wish you all happy learning experience. Thank you so much. Jai Hind.
Thank you, Vyas sir. And next, we will have an enlightening words from our Honorable Vice Chancellor sir, Professor A.W. Santosh Kumar sir. Sir, I request you to please enlighten us. Thank you.
Good morning, everyone. Respected Selamurthy sir, President, Amity Science, Technology and Innovation Foundation. I'm the Chancellor of Amity University, Chhattisgarh. The dignitaries from Amity University campus, Registrar, the Dean Academic Affairs, the HOIs, the head Center for Nanotechnology and the convener, Dr. Latte, and co-convener, Dr. Arif, all the participants, researchers. The international workshop that ran for 3 days on deciphering the recent trends in functional nanomaterial and technological applications is indeed an adept title, where currently we have speakers spanning from 6 different countries in the world, starting from US, Germany, South Korea, Taiwan, and Saudi Arabia. And as already mentioned, this plethora of speakers will be touching upon in many facets of nanotechnology. As we all know that the buzzword nano is always now an addendum for every discipline. Take it medicine, now it is nanomedicine. Take it agriculture, it is nano-agriculture. So this term is being sufficed and prefaced in both the places where this technology and the know-how becomes a very great innovation that is being implemented. And studying the technological application part is indeed very important as we move on to a research and innovation-driven country, India. All the funding agencies as well as the learned forums and academia are only focusing on the application of the new knowledge that we have given to the students. So it's indeed a great pleasure that we have a very great visionary who had mentored this kind of innovative cutting edge technologies 2 decades ago. Our founder president, Dr. Azim Chavan, had been put forth a lot of new innovative institutes, research institutes, which is very unique of its kind that you would never ever see in any big academia. Through his spearheading force, we have our founder, we have our chancellor president, Dr. Azim Chavan, a product from Wharton Institute, spearheading the goals and the legacy of our founder president, who is the main linchpin behind the Amity universities in bringing forward research and innovation technology. The faculty members, the student friends, it's indeed a very great honor that we have Center for Nanotechnology here at Amity University of Mumbai. And we have scientists who are focusing on cutting edge technologies. And I should certainly say and endorse here, we have Dr. Latte, who's being designated one among the 2% scientists in the world with a lot of his cutting edge innovations, his publications. And none the least, Dr. Arif, who had joined the team very recently, is being profusely funded by Department of Science and Technology. So at this outset, I really congratulate and wish a great success in bringing about culminating this new knowledge, and the deliberations will be a great success and will take a mile forward and will be certainly a feather in the cap of Amity University. Thank you very much.
Thank you, sir, for those kind words. And with this, having the blessings from Dr. Selvamurthy sir, Dr. Santosh Kumar sir, Vyas sir, and Zarate sir, we will move on to the next session as we have promised. This session consists of 5 talks from different international speakers from all over the world who will enlighten us and provide us and give you a glimpse of different fields of nanoscience and nanotechnology. They will be introducing us to the various aspects of nanoscience and nanotechnology. This session will be chaired by Dr. Praveen Walke sir and Dr. Suhas Zezulkar sir from University of Mumbai. I request Dr. Dattatreya Latte sir to give a brief introduction of the session chairs to all of us. Latte sir.
Okay.
Thank you.
Yeah, thank you, madam. Dr. Praveen Walke has completed his PhD from Italy in 2000, and afterwards he then returned back. He has joined Savitribai Phule University for some time, And since last 5 years, he is working at University of Mumbai at Center for Nanoscience and Nanotechnology. He is a leading researcher in the field of field effect transistor, 2D materials, inorganic cleared materials, and he is also a good collaborator to our Amity University, Mumbai. We have another session chair, Dr. Suhas Jejurikar, who has completed his PhD from Savitribai Phule University. Afterwards, he worked at France, UK, many countries, and returned back and joined University of Mumbai as a faculty. Dr. Walke and Jejurikar are joining shortly, as they are facing some issue with the network. Dr. Walke, are you here? I just talked to him. He's facing some network. So I think without wasting time, I'll just call our first speaker, Dr. Pawan Kumar Tripathi. Already he is here. He has completed his PhD degree recently, and then he is currently working in a Case Western Reserve University, Langland, Ohio, USA. He'll be talking on temperature-dependent superplasticity and centering the copper, nickel, chromium, FeMn high entropy alloy nanowires using this atomistic simulation. I request now Dr. Pawan Kumar to share his screen and to start his lecture. Dr. Pawan Kumar, over to you.
Okay, so hello everyone. Am I audible?
Yes. Just make
okay, so
full screen. Yeah.
Yeah.
Make full
So
screen.
yeah. So I'll be doing that. So thank you very much for inviting me for this lecture. And yeah. And so first of all, like I want to thank all the organizers and Dr. Dattatreya Latte for giving me this opportunity to just discuss about my work here. So I am Pawan Kumar Tripathi. I'm currently a postdoc at SDLE Research Center in Department of Material Science and Engineering at Case Western Reserve University, Cleveland, USA. So I'll be just talking about today like some temperature dependence of like superplasticity and strengthening in like high entropy alloy nanowires. So that this study is based on atomistic simulations. So just a little bit about myself, like I finished my PhD from IIT Kanpur and NCTU Taiwan. Like I got a dual degree and then I moved to Case Western here. So just giving an outline of my presentation today is like I'll be just first introducing about nanowires and then a little bit about high entropy alloys and then high entropy alloy nanowires. And then the like deformation behavior of high entropy alloy nanowires. Yeah. So nanowires, like they are now everywhere. So they exhibit like unique mechanical, optical, and electronic properties, and they're like a high aspect ratio and a single crystal structure. So they're like material properties. Generally, they differ significantly from their bulk counterpart due to their large surface area. So I don't know, like why it's not working somehow. Yeah, so many metallic and semiconducting nanowires have been synthesized in the experiments, and their applications are like ranging from nanoelectronic devices. They are used as connectors for the transportation of electrons, and they're also nowadays being used in screening drugs for neurological diseases. They are also in nanoscale quantum devices as like field emitters, and they are also used like to build transistors without like PN junctions. So so far, like there are like many single element nanowires have been synthesized, and they are being utilized in the different industries and for like their diverse applications. So today, like I'll be talking about first like high entropy alloys. So like what are they? Like they are like solid solution alloys. So well, like they are like so in general, like in an alloy, like two or more elements are mixed in such a way that they form like a kind of mixture. And in high entropy alloy, so they generally constitute a single phase crystal structure, and each element of that alloy is between 5 to 35% like that. And they usually have like superior properties than conventional alloys. So that's the like main purpose of synthesizing these high entropy alloys. So they have like high strength, thermal stability, the fatigue resistance, their wear resistance, and then their corrosion resistance. So they have like all these superior properties than conventional alloys. So the core effects of HER, they are called like sluggish diffusion effect, and they have like severe lattice distortion because the different elements, they have like different atomic diameters, and that's how their like electron clouds, they differ with each other. So they have like this cocktail effect because of like different kind of bonds between the constituent elements. So they have like a simple solid solution instead of like forming like complex phases or intermetallic compounds. So it's so because of like their high mixing entropies and sluggish diffusion, so it generally like decreases the brittleness of the material. So we get the right ductility which is required. So they are also used in like high temperature applications because of their high thermal stability, and their oxidation resistance is also exceptional. And the mechanical properties, which are such as like high temperature strength and thermal fatigue. So these are all like enabled by compositional and structural features of high entropy alloys. So nowadays, like their mass, so they are like high entropy alloys. They are like first, discussed like during 2004 or 5 from JWA and Cantor. So they first proposed a high entropy alloy called Cantor alloy. This is like constituting like 5 different elements: the cobalt, chromium, iron, manganese, nickel. So that was a mixture of all these. And so their applications are like now ranging in different industries, like nuclear industry, in aerospace, for like coating materials. So more than 300 high entropy alloys like were reportedly processed so far with more than 30 elements. So they generally forms a solid solution. And for this particular high entropy alloy, it's like FCC crystalline structure. So now coming to high entropy alloy nanowires. So high entropy alloy bulk like are also there, and they have like unique properties. But if we go to the nanoscale for this high entropy alloy, so this recently these are also being synthesized like one of the study from Pavitra et al. They talk about this particular high entropy alloy, which nanowire, which has been synthesized in the lab. And so it also like possesses high temperature structural stability and excellent balance between strength and ductility. So particularly at cryogenic temperatures. So that is like typically 77 K. So here like 5 primary elements that ranges between 5 to 35% for each elements. So these are like some images from their SEM and characterization. So if we talk about the mechanical behavior of these high entropy alloys, so generally like damage tolerance is arguably the most important mechanical property because of like for the design applications of structural materials. So what is like damage tolerance? It's a like combination of strength and toughness. So which is a like ability of a material to resist fracture. So this toughness is generally governed by, if you go to the atomic scale, it is governed by easy motion and multiplication of dislocations, which is a kind of material defect. So that like compromises somehow the strength. And at low temperatures, generally in the materials, the dislocation glide is like primary deformation mechanism. So the moment of dislocations, generally this takes place by locally breaking and reforming the bonds. And that's how like it governs like the different mechanical properties of the material, high entropy alloys specifically. So like if you want to develop like required mechanical strength in a particular material, or say like for this context, the high entropy alloy nanowire, we have to like say we want to like add some alloying atoms. And so the solid atoms, they locally introduce different kind of crystal bonds with different mechanical strength. So they cause like a lattice distortion, which offers somehow like resistance to the dislocation motion, which results in like in enhanced strength and reduced ductility. So that's like the typical way of alloying. But in case of high entropy alloy, this like display excellent mechanical strength because it is generally in a single phase, and the like say tensile strength is around like 1 gigapascal, and ductilities are also significant, that is 60 to 70%. So for a material having a proper enough strength and ductility, that's like the goal of the engineers, which they look for. And this fracture toughness also is exceeding like more than 200 megapascal root meter. And then this hydropel alloy has like low stacking fault energy, which is also good thing. And then these like properties are comparable to like very best cryogenic steels. So they are like austenitic stainless steel, high nickel steels. So these are like comparable to that. So coming to the deformation mechanism of this hydropel alloys, so at low strains, so generally a planar dislocation glide happens. So I'm not sure like whether like people are the audience, they are like have a background in the material science. I mean, these are like particular atomic mechanism which takes place and at the atomic scale, and they govern the like materials properties somehow. So if there is a like perfect dislocation, this splits into like Shockley partials. So those are like another kind of dislocations. And at high strains, generally the nano twinning becomes an additional deformation mechanism, so which is a combination of dislocation, slip, and twinning. So this provides a steady source of strain hardening, which somehow inhibit necking and which delays the onset of necking, and that the like ductility enhances together with the strength. So this has like excellent toughness, as also seen in like tuning in this plasticity steels. So the current work is like attempts to understand the mechanical behavior of hydropel and NOS, and it also talks about like this temperature dependent strengthening and superplasticity. So in this work, like I have mainly used atomistic simulations, which is implemented in LAMPS, that's like a molecular dynamics package. So and then we'll talk about like the fundamental mechanism of damage tolerance and mechanical behavior here. So so these are the nanowires like which I have like simulated for their mechanical testing. So I choose like one single element nanowire, that's like a silver nanowire, and another is like high entropy alloy nanowire, where like the 5 different elements are there. And so I choose like this like enough aspect ratio, and so we use like molecular dynamic simulation here, and that is implemented in LAMPS. And for both silver and high entropy alloy nanowires, we use like different interatomic potentials. So for silver, we use like Williams and Mason's potential, that is like embedded atom method potential. And for high entropy alloy, we use like second nearest neighbor modified embedded atom method potential. And so at 3 different temperatures, like ranging from cryogenic, that is 77 K, and the room temperature, and the high temperatures. So at these 3 temperatures, like I perform the like mechanical deformation, and then try to reveal the atomistic mechanical properties. So these are the like orientations and some other details about this simulation box. And the X, Y, and G, like they are all periodic. And then there is a like around 100 angstrom vacuum in X and Y directions, so that the 2 images of this simulation cell, they do not interact. So then this tensile deformation was applied along G direction, and the strain rate was 10 to the power 8 per second, like 0.001 fem per second time step. So if we see here, so these 3 are like at different temperatures, like one is at 77 K, and like the figure B is at room temperature 300 K. So at 77 K, what happens, like the SS curve for silver nanowire, this shows like 2 peaks indicating yielding of the 2 phases. So if we go to this blue curve, it shows like the 2 yielding behavior here. And so what happens here, like when we start stretching this nanowire, when you start applying this tensile load in this Z direction here, so so generally like the free surface of the nanowires, they are like preferential nucleation sites of the dislocations. So here we first get a stacking fault, like which like on further application of load, it converts into 2 twin boundaries. And then the area between these 2 twin boundaries converts into a different phase. So like kind of phase transformation happens. And so eventually like the whole nanowire gets converted into a different phase. So the 110 direction of this nanowire the 110 phase of this nanowire converts into 100, and then eventually it fails with this dislocation slip. When we go to like higher temperatures, so this phenomena is just somehow diminishing, and we have like another mechanisms which are operative at high temperatures. So if we see like at very high temperatures, they're like many different like nucleation of these partial dislocations, so which are also contributing to this deformation behavior. So this is also evident from this stress strain behavior, and these serrations seen in this stress strain curve, they are because of like this nucleation of different like partial dislocations here. So how do we characterize these dislocations? So in well, like these two HCPs like atomic layers are stacked together. This is called a like intrinsic stacking fault. And when there is a like one atomic layer gap, that is called like extrinsic stacking fault. And when we have like more than one atomic layer gap, that is called like a twin boundary gap here. And when like the many like HCP layers are accumulated, this is called like an HCP phase here. So here is an animation at cryogenic temperature, like how does it deforms. So generally like this nucleation and propagation of this, so when like this partial dislocation that takes place from the free surface, so you can see like the area between these two like stacking faults between these two twin boundaries is transforming to a different phase from like 110 to 100. And once this finishes up, like on further application of load, it generally fails via dislocation slip. So at high temperature, this motion of twin boundary is retarded due to like thermal vibrations. This phase transformation is mainly driven by the surface stresses, which enable the reduction in the surface energy. And now if we talk about like high entropy alloy nanowires, so here what happens, the same phenomena like takes place at the room temperature, but in addition to at cryogenic temperature. In addition to that, like we have a few more mechanisms which are operable at like all these temperatures. So like when we start applying the load, the stress strain goes in the like proportional way, and then this is not completely linear. It becomes somehow like non-linear, and then at like the very first yielding behavior, we see like the first kind of nucleation, dislocation nucleation here, and then there are like some continuous nucleation of dislocations, which can also be seen here with this red dislocations in this right side of figure. And then this abrupt change of this stress behavior is also that can be seen here as a like twinning boundary, twin boundary creation. And so when this twin boundary starts moving, and because of like interactions from the nearby dislocations, they form somehow like a lumbar quadrille locks, so which retards this motion. So that's how like we get this additional like plasticity here. So this nucleation of partial dislocations like continues even after this twin formation, and so this is mainly because of this lattice distortion effect that is amplified at higher temperatures also. So at high temperature, we see like these nucleation events are more, and they are responsible for like this martensitic transformation. So if we go to like 300 Kelvin, so here we can see there are like more incidents of this nucleation. And in addition to that, these lumbar quadrille locks, they are somehow unlocked if we go to the like higher strain levels. So, and eventually this fails via like a combination of like two mechanisms, like the martensitic transformation and dislocation slip. And if you go to the very high temperature, that is like at 1000 Kelvin, it still shows like considerable like strength, like in so that is like opposed to the silver nanowire, where it fails like very quickly. So here we can see a like remarkable refractory property of this high entropy alloy nanowire. So so this is like deformation behavior of high entropy alloy nanowire, where like we see like there are multiple events occurring, and so because of this, the complete reorientation of this nanowire is not possible. So here we can see like these are like parallel nucleations events, and then there are like these locks they form, and then this does not allow to transform this like a nanowire from one phase to another phase. So this phase transformation is difficult, and then like other mechanisms are also operative at So this like interaction of like this leading and trailing partial dislocation, they result into this lower quadral locks, and they are inherently responsible for the work hardening behavior here. So increase in fraction of this HCV phase results into unlocking of lower quadral locks. So if you see the bottom right figure here, these locks are getting unlocked. And this is like their crystallographic mechanism, like how they form. And then there are like some immobile dislocations form, they call like stair rods. So they are also present here. And this is the dislocation density, like estimated at different stages based on their nucleation and annihilation rate. So at cryogenic temperature, there is like high dislocation activity, and at high temperature, so there is like no dislocation activity at all. I mean, there is like very little dislocation activity. So and if we see like if we compare the stress strain behavior of a silver nanowire and hydropolar nanowire, we can see the hydropolar nanowire strength is always greater than the single element silver nanowire, and we can also see a significant amount of this is stress strain curve area, which is responsible for the toughness and eventually for also for damage tolerance. So if we talk about like the fraction of atoms at different strain levels, so we can see like this BCC and like the FCC atoms, they try to reduce, and HCP atoms they start increasing, and then after some time they become like stagnant. And in case of and if we see at like high temperatures, like in the hydropolar nanowires, there is like a lot of phase transformation taking place. So that's why like at 1000 K, you can see a lot of HCP atoms are also present there. So this partial dislocation nucleation promotes like temperature dependent synergistic FCC HCP martensitic transformation during the later stage of tensile deformation. So these are like some numbers from the some different work so of like stacking fault energy. So there are like some criteria based on these different like stacking fault energies. So they predict about tunability and partial dislocation nucleation rates. So this like work generally promotes. I mean, this is in a good accordance with this with these like studies. So the deformation mechanism of hydropolar nanowires at different temperatures, like so the easy formation of dislocation is because of a severe lattice distortion in the hydropolar alloy, and the low stacking fault energy of hydropolar alloys generally is responsible for the low stacking fault energy is promoting the twinning behavior. And the twins, which are nucleated from the free surface, they accumulate and form HCP phase, which blocks the motion of the twin boundary in contrast to the silver nanowires. And at high temperature, most of the FCC phase convert into the HCP phase, which result in the brittle fracture due to reduced slip system. So the conclusion is that like both silver and hydropolar nanowires, they show unique superplastic behavior during tensile deformation at like cryogenic temperature. And for silver, the deformation mechanism is mainly twin, which is tuning induced plasticity, while in hydropolar we can see like a synergistic sequence of like both tuning induced plasticity and FCC HCP martensitic transformation. And if you go to the room temperature, the like formation of lower quadral locks that promotes like formation of nucleation sites for the HCP plus phase transformation. And at the later stage of deformation, this FCC to HCP martensitic transformation that causes like unlocking or annihilation of the lower quadral locks. And if you go to the high temperatures, this FCC to HCP martensitic transformation that dominates in hydropolar, so which results in a like transformation induced plasticity kind of behavior. which enables like additional ductility and refractory properties. So we can conclude that this synergistic sequence of like this plastic deformation mechanism in high entropy alloy at different stages of like strain are the source of its excellent combination of strength, ductility, and toughness or damage tolerance. So yeah, so these are some acknowledgement and any questions or suggestions.
Professor Suhas Jujulkar, session is open for question and answer.
Yeah. So what's the question?
Okay, Paul, I have a question. Okay, diameter dependent studies on the silver nanoparticle has been done already, or what is the relation with the diameter?
Yeah, so I think there are like many studies based on this nanowire diameters, because this aspect ratio is also responsible for like different mechanical properties. So I mean, there are like both experimental and simulation studies are available, and this has like the diameter of nanowires have like a direct relation with the mechanical behavior, the mechanical properties like UTS, the ultimate tensile strength, and the yielding strength. So they are all related to this diameter. So as you go to so there is a like threshold diameter. If you go below that, I mean the strength is going to improve, and after threshold limit, it is not going to further increase. So that's the relation.
Okay, okay. Is there any experimental report on cobalt, nickel, chromium, iron, this manganese?
Yeah, so yeah, so actually there are like few studies which are not on exactly this alloy, but I mean the 4 elements of this alloy are present in some of the experimental studies, but not like all. So this was like the first high entropy alloy, which was proposed by first like Ye and Cantor. So I mean there is so far like no, like in my knowledge, like there is no such study, but maybe like it is very soon possible that people will start using high entropy alloy nanowires for different applications.
Okay. I think there is one more question in a chat box.
Okay,
I can read for you.
Yeah.
So can a combination of platinum and gold or gold and silver to reduce the lumbar critical lock effect so that the deformation strength can be increased, and at a cryogenic temperature also there is no breakage in the wire, right? So can you?
Yeah. So that will like depend first. So I mean, in the simulation, it is possible that we can add like whatever we want, but the experimental conditions are quite different. So it will depend on their mixing entropies and some other factors, like how this platinum and gold can be mixed together to make that alloy. So here, like for high entropy alloys, like we have like at least 4 or 5 elements. But like in a general alloy, I mean, you can mix in theory in in simulations, but for the experiments, like I'm not sure like whether that is going to happen or not. So of course we can use brass alloy, but that is not a high entropy alloy.
Okay, we have one more question. A question by Dr. Bharti Patil. Bharti Patil, doctor, you can unmute and ask your question.
Mm-hmm. Yeah, sure.
Hello.
Hi.
Hello. Good morning, sir.
Good morning.
Sir, I wish to ask you the question that these materials are going to be highly unstable, no?
Which one?
High entropy alloys.
No, they are not going to be highly unstable because so they crystallize in a single phase crystal structure. So that's how like their Gibbs free energy is minimum. So they are not highly unstable. They are being synthesized. So based
okay.
So if yeah.
And sir, one more question is that suppose I am synthesizing one material, but at present I don't know whether it is coming under a high entropy alloy or not. Then what is the test that will define me that given material or this material synthesized by me is a high entropy alloy?
Yeah, so I think that is if you know like some materials thermodynamics, and then based on like Gibbs phase rule, you can decide like you can just try to get the like from the phase diagram, you can try to get the mixing entropy and then the respective enthalpies, and then try to calculate like Gibbs free energy. And if it is like minimum at some point, so that is going to be stable at that particular phase or temperature.
Okay, thank you very much, sir. Thank you.
Yeah.
We have one more question by Dr. Pratiksha. Pratiksha, you can unmute and ask your question.
Yeah, sure.
Pratiksha.
So I just want to ask you that in the beginning you told us that this experiment of Ag and the Pavitra element has been carried out in vacuum medium. So will the nanoparticle act similar way in the normal conditions also? Because vacuum, we know that it is a complete different condition. There is no effect of air or any other environmental changes happening on it. So will the experiment be same when we carry out in normal atmosphere or without vacuum medium?
No, I think that should not be the same, because like we always have some effects from the like atmospheric, from the atmospheric conditions. So those are not going to be same. So that's for sure. But like once they are synthesized, and so we use like I mean to make them usable, like we have like certain checks which are there like to like before they are actually tested on some actual applications. So I mean it's they are not definitely not going to be same like if they are in vacuum or in some other conditions. So like in the very first attempts, like people generally try to synthesize them like in their best possible environment. So that's the case.
Okay, sir. And sir, I want to ask you like how we are using alloy for making the wire. For other such nanomaterials, we know that nowadays we use carbon nanotubes mostly, which is a combination of fluorine and graphene. So in that way, we can use any other allotropes also for formation of new nanoparticles, so that this deformation effect can be reduced.
Which deformation you mean?
Means now we have seen that while studying alloy, Lomer-Cottrell lock, due to which the deformation of wire takes place. Then is this condition applicable for allotropes used also, if we use?
No, so here the Lomer-Cottrell locks, they are not assisting the deformation. They are just hindering the motion of the dislocations. So so generally this dislocation motion, they provide some additional like mechanical properties to the nanowires, or like for any material, like generally if you go to the like any material which is like ductile enough, when they fails, so this dislocation motion is generally responsible for their so it's not like the actual cause, but it affects the way they deform. So their motion is not like I mean so Lomer-Cottrell locks, they are not responsible for the deformation. They just hinder the dislocation behavior, dislocation motion, and that like enhances somehow the mechanical properties. So our goal is not to get rid of that lock kind of things, because those are like some inherent like very unique properties. So I mean they are like just to be engineered in a way so that we have like the right combination of strength and the ductility.
Okay, so thank you very much, sir.
Yeah.
Okay, any more question? Okay, if there is no question, let's thank Dr. Pawan Tripathi, joined from USA. It's midnight for him. Thank you, Dr. Pawan Kumar, for giving very excellent lecture. Thank you. Thank you very much.
Thank you so much, Dr. Dattatreya. Yeah, it's like around 1 a.m. here. So yeah, so it's a midnight time here.
You.
Yeah.
Thank you very much. Thank you. Okay. We move to next speaker. We have Professor Sandeep Shinde with us. Sandeep Shinde has done his PhD, MSc from Savitribai Phule Pune University, and then PhD from South Korea. Then 2010 he has returned and joined a biotech company in Bangalore. Then afterwards in 2012-13 he joined Ramanujan National Fellow at CSIR National Chemical Laboratory. Afterwards he was a faculty member at ICT Janna campus, and afterwards he joined as an Alexander Fellow in Germany, and he is currently working in Germany. Today we'll be talking on progress of nucleophilic fluorination using some of these metal fluorine protein catalysis for environmental application. Professor Sandeep Shinde, the mic is yours. Sandeep,
hello, can you hear me?
Voice is not. Yeah.
Yes, we can hear. Yes.
Yeah.
You can see my screen. Yes, we can see.
We can hear you now. Yeah.
Okay. Thank you very much, Dr. Latte, for the nice introduction. I would like to today give my presentation under the title of Progress of Nucleophilic Fluorination using the nanometal fluorides in protein catalyst environment. So, as we know, the fluorine is very important in our daily life. We use so many things, many utensils that can. Hello.
Yes. Sorry to interrupt. Can you go to presentation mode, please, so that it is better to audience?
Wait.
Go to full screen mode.
Currently, it's not full screen.
No.
It's full screen now.
No, sir.
Just press it. Yes. I think still it is not there. But if it is not, then you can just increase the percentage so that we can see the maximum screen.
And now?
Slightly better, yes. No, just go a little back. Go back. I think we will just reduce this percentage. Reduce it because.
Okay.
Yeah, slightly better it is now. Okay.
Can I go ahead? Hello.
Yes, sir.
Yeah.
You can continue if there is no problem. You can continue.
Okay. So as we know that there is a very importance in fluorine, like we are using the pan that's coated with the polytetra fluoroethylene, that is we call Teflon. So non-stick we can use for like preparing dosha or like any pancake like that. And also fluorine also present in some water, and also in the toothpaste we use for the sodium monochlorophosphate to protect the decay. Usually the children's, they use such kind of fluorinated toothpaste to protect their cavities. Also, the fluorine is very important in the medical sections. It is in medicine they use for the radio labeling of fluorine by using the various fluorination technology and detect the diseases, and particularly it helps to diagnose the Alzheimer's disease, which is found in the old age people. Usually they lost their memories, and this progress of this disease can be diagnosed or identified using the FDG. This is you can see the structures, this fluorinating labeled. So it is a very important fluorine in the various sections in area of research. The fluorine is very important due to this high energy and used in the lithium-ion battery, pharmaceutical and chemical lasers. Actually, the fluorine and the hydrogen bond are equal lengths, so it is very lowest steric hindrance when it's exchanged with hydrogen with fluorine. So that help does not change the activity of any normal drug molecule which can exchange with fluorine with replace with hydrogen. And also, if you introduce fluorine, it's increase the lipophility of the molecule, and it helps to enter into the fat solubility. Also, the active potency and activity and stability of the compounds. So this is the advantage of the fluorine introduced into the drug molecule. And as I said, that fluorine 18 is very useful in the positron emission tomography to identify the various cancer diseases, and we can detect it in early stage, so we can give the treatment to the patients. And currently in India, there are the almost, I think, 8 PET scans are available in the various hospitals in metro cities like New Delhi, Pune, and Mumbai. So it is emerging field in the medicinal research. So we can see that fluorine actually, when you want to introduce in the organic molecule, which requires, it can act as a bifunctional, like it will act sometimes is nucleophile, and then it give the fluorinated product. But you know that fluorine negativity is very high, so sometimes it act as a, like a base, and which can reduce the, which can abstract the proton instead of introduction the fluorine and give the side product olefin. So it directly affect on the your product selectivity of product fluorination, and also it affect on your yield. So therefore, Professor Chi in his research, he has developed a fluorination method by using the ionic liquid, and you can see in the first reactions here they use the water molecule, and that water molecule is protic atmosphere, which can give the selectivity of fluorination and give the yield 94%. This is because of the presence of water. And similarly, he has developed another method which use the fluorination, fluorine 18, to introduce the fluorine 18 molecule. So he also improved, this is a 93% yield, which can be achieved due to the presence of water and a protic atmosphere. Therefore, he, instead of water, usually give the byproduct alcohol. Therefore, he has introduced another media like a tertiary alcohol. That tertiary alcohol also is like a protic solvent, which can use for the many reactions. But usually the fluorinations, when we conduct with the tertiary alcohol moiety, it gives the fluorine rate product more, and the byproduct alkene significantly reduced. So it gives the 93% conversion, as we can see. So similarly, this effect of the protic atmosphere, how it affect, we have found out the reason. So you can see in section A, the selective solution of fluoride by hydrogen bonding. The tertiary alcohol moiety is contain the alcohol, which can interact with the fluorine of cesium fluoride and try to reduce this bond function by the hydrogen bonding, and detach this fluorine from the cesium, because it's the cesium, you know, that is bulky alkyl metal, and then when it this fluoride is form a light hydrogen bonding with fluorine with alcohol of tertiary butanol, and it is like a flexible fluoride. It reduces the basicity of the fluorine. And then you can see the D sections where it's significantly interact the hydrogen bonding with your fluorides, and also the presence of oxygens of leaving group sulfonate, and directly attack this fluoride selectively, and does not abstract the fluorine due to this attached to the all hydrogen bonding. It does not act like base. So therefore, it reduced the chances to formation of the olefin. So in this fashion, due to these considerations, we have designed another protic solvent that's using the ionic liquid and tertiary alcohol moiety. So you can see the structures we have designed, like one alcohol one side, tertiary alcohol moiety, which carrying the ionic liquid. Ionic liquid is important because it can help to solubility of metal salts. So because you know that ionic liquid can soluble many salts easily, like similar like water. So that's why we designed this protic ionic liquid. The synthetic method is simply by epoxide is treated with imidazole and then treated with alkali missile 90 degree, and then you can get this desired ionic liquids. In this research, we synthesized two ionic liquids, like instead of substitute side chain of methyl, isopropyl, butyl, and uh, hexyl side chain, and see its reactivity into the fluorination reactions. Here, we perform that reactions by using the methyl substrate, cesium fluoride 5 equivalent, and that we synthesize this ionic liquid for and then 100 degree temperature, and all reactions were stopped at 15 minutes. So first you can see the entry that methyl substituents like side chain, which contain the methyl and then alcohol moiety, and this 5 equivalent. You can see the 100% conversion, and in bracket we see this 97%, which is isolated, but 100% it is determined by using the proton NMR. We did not see any byproduct formation like olefin or any alcohol. So this is the very promising result. Then we checked other synthesized ionic liquid like propyl side chain, butyl, hexyl side chain, and then we see the result. We found that this hexyl side chain, if it is present, it gives the remain unreacted starting material and give the only 56%. But when we reduce the side chain with alkyl group like butyl, propyl, it gives the 85% up to 85% conversion. But very less presence of methyl like alkyl group gives the higher conversion. So also we have checked whether it will act as a equivalent if we increase, which can improve the more yield, or it can affect on side product formation that we have tested. And you can see the entry 5, we have used 3 equivalent of that's promising ionic liquid, and it gives the 93% conversion and reduce the formation of byproduct olefin. You can see here. So this is the impact due to the high solubility of ionic cesium fluoride salt. Similarly, we use as a solvent this ionic liquid, and we have tested its product conversion without any acetonitrile or without any other solvent. We used only this ionic liquid, and we found that 84% conversion. Similarly, it gives significantly, it gives the olefin formation, also the formation of new byproduct, that is alcohol. Means they attach this methyl group with hydrogen. So this is the impact of increase the solvent or amount of the ionic liquid. Also, we tested whether really it require the ionic liquid moiety attached to the tertiary butanol. Therefore, we conduct one reaction with only tertiary butanol solvent with like 0.5 equivalent, and we can see the 76% starting material is remain. So it indicates that the ionic liquid moiety is very important in this catalyst attached to the tertiary alcohol moiety. That impact give the more conversion like 100%. And in another way, whether really we need to synthesize this ionic liquid, or we can use the similar equivalent of ionic liquid plus tertiary alcohol moiety. Therefore, we conduct reaction entry 8, and then 5.5 half of equivalent of commercially available ionic liquid and tertiary butanol solvent, and then we can see the 58% starting material is remain. So only 40% conversions we found. So this indicates that the formation of this methyl imidazole ionic liquid increase the reactivity of fluoride. So here we checked its substrate scope, whether we can use this one for the other substrate. As here we use the leaving group triplet, And using the normal condition A means like using the tertiary butanol solvent, you can see 300 minutes it required for the reaction and 94% conversion. And also it formed the trace amount of other byproduct, that is ether, means two molecules bind each other. And here reaction B, here we use the only ionic liquid. Reaction goes very fast, but you can see the alcohol formation side product, 91% conversion. But in the case of C entry 3, that we can see same time like 1 hour, the reaction give the 97% conversion, because this ionic liquid has unique reactivity, contain the ionic moiety as well as protic tertiary alcohol moiety around the catalyst, and that increases the 97% conversion. When we checked another substrate which is having the different positions in the leaving group, it is secondary positions, tosylate. You can see this give the 94% conversion, usually reduce the olefin formation. It is very difficult to convert the secondary leaving group to get the selectivity. Always it gives the byproduct formation. You can see the entry 1A and B, 4 and 5, using the tertiary butanol and ionic liquid. It gives the olefin as well as alcohol and ether byproducts. So these are really impact on the radiolabeling cases or in the fluorination. And here this is the another steroid molecule we have tested with fluorination, and it gives the 94% with our catalyst. So in these passions, we concluded that one, okay, the mechanism of this formation is that usually this tertiary alcohol moiety, you can see in this left side figure, this fluorine interact with the alcohol moiety with hydrogen bonding. It does not act as like a base and does not abstract this proton, and therefore it reduces the formation of olefin, but it significantly, due to this hydrogen bonding, reduce the basicity and enhance the fluorination nucleophilicity and improve the selectivity product formation. So this also we have studied. After this promising result, we turn our attentions whether we can use the nanomaterials for these fluorination reactions. And here we have obtained the from my colleagues with collaboration with Dr. Latte, we obtained the molybdenum trioxide nanoparticles, and we have tested its fluorination reactions using the various conditions. These nanoparticles, you can see the morphology, same morphology images, that you can see the nanosheets represent, and this is B1 is nanosphere, easily you can see, and nanorods. These are the synthesized by different methods, which is reported as isothermal method, solvothermal methods, and hydrothermal methods. So in this fashion, we use these three nano molybdenum oxide nanoparticles for the fluorination reactions. Here we perform the fluorination reactions, and the results are shown in this table. Usually this is the one mesylate. It can treat with a cesium fluoride, which we use for the regular fluorination reactions, and whatever the nanocatalyst we use, that here, and the solvent we use usually the acetonitrile and slight amount of water, which can make the like a protic atmosphere to increase the selective fluorinations. And then here you can see the entry 1 is 18 crown ether, which is a common catalyst which used for the fluorinations, which does not have any protic atmosphere. So here you can see the 12% conversion and very less amount of the other byproduct formation. And here, if we use the water in that reaction, it does not form any product. We can see very tiny amounts of selective fluorinations and very trace amount of byproducts. But in case of we use the commercially available molybdenum oxide, and then without any water, you can see the 20% conversion. But when you use the same commercially available molybdenum oxide with some amount of 180 microliter of water in the 380 acetonitrile solvent, you can see the conversion, 56% conversion. So this is the promising result. That's why we tested our nano catalyst A, B, and C, and you can see A is like a nano sheets, and B is nanosphere, and the C is nanorod amorphous like morphology of this nano catalyst. And you can see the NT7 gives the 88% conversion, which is more higher than the other remaining catalyst. It gives the trace amount of olefin as well as little amount of alcohol that may be due to the presence of water. And here we change the variations of this catalyst concentrations of nano rods, and then we see the conversion, and best found that one we use if like 10 more % of this nano catalyst and 180 microliter water, and 1.5 hour reactions give the 88% conversion. So based on this result, we have conducted its scope of this catalyst for the various substrate. Here we use the various leaving group like 5-triflate leaving group and the tosylate as a leaving group for the fluorination reaction, and the nozzolate, mesylate, and iodine. These are the commonly used leaving group for the nucleophilic substitution reactions or any fluorination reactions. So here we choose the catalyst C, which is having the morphology and nano rod shape, and acetonitrile solvent, and similarly water and 100-degree temperature, and all reactions were stopped at 1.5 hours later and found the result. Here you can see comparative table like leaving groups effect. You can see the tosylate, it gives the 90% or 91% conversion comparatively with other leaving groups like triflate and nozzolate. Similarly, like aliphatic fluorine, it gives the fluorination 71%, and then this is the like 80% of fluorine. Here also like as sugars molecule fluorine, it gives the 83% conversion, but it takes longer time, like 2.5 hours. Like another leaving group like triflate with this heterocyclic compound also give the 48% conversion. Because this kind of directly attached leaving group to the nitrogen atom, it gives the alcohol byproduct. So almost we got little good yield compared to the other reactions, other catalyzed reactions. So here we found this primary alcohols, primary leaving groups like 12A, 13, and 14. It gives the like almost above 80% convergence. And here secondary leaving group, which is like 15A, is like a triflate leaving group, secondary triflate, which gives the 58% conversion. But secondary, it's present secondary, that's it takes longer time because of the low reactivity of this compound and low solubility in the acetonitrile. Therefore, it impact on the conversion, and it gives the 58% product after 6 hours. Similarly, another secondary leaving group, it gives the 2.5 hours, 73% conversion. But when we see the directly attached to aromatic system triflate for 18A, it does not show any reactivity. So aromatic reactivity is still challenging, and we are working on this one still to get the aromatic fluorinations by using the nano catalyst. And based on this result, we concluded this what is the possible mechanism of these reactions, how it interact with the nano catalyst, and how it improve the reactivity. As we know, the leaving group contain the sulfonate moiety as having the oxygen atmosphere and also water molecule that can interact on the surface of the molybdenum oxide nanoparticles, and which can form the little hydrogen bondings type interactions with molybdenum nanoparticle, and which will enhance the reactivity of fluoride and also improve the leaving group ability of sulfonate. And this is the reason we found that one nanocatalyst can be used for the organic transformations. In conclusion, I would like to say like this protic atmospheric of tertiary alcohol, like synergic effect of two solvents like tertiary alcohol and ionic liquid enhance the nucleophilicity of fluoride by hydrogen bonding. And efficient molybdenum oxide catalyst can be used for the nucleophilic fluorination reactions. And we found that one comparatively morphology, rod-shaped morphology of molybdenum oxide, which gives the good reactivity compared to the other known catalysts like crown ether or other known commercial catalyst. And also it's significantly reduce the reaction time and improve the selectivity compared to the other catalyst. And finally, I would like to thank for the organizing committee, VC Dr. Santosh Kumar sir and Honorable Chancellor Asim Chavan sir of Amethi University. And also I am very much thankful for the Dr. Latte for inviting for this an international conference and organizing committee. And also I am very much thankful for this funding agencies that given me allow me to do the research. Without their funding source, it is very difficult to perform the research. And finally, thank you very much for kind attentions.
Thank you, Professor Sandeep, for very nice talk. Now session is open for a question. Participant, they can. Yeah, Pratik says, go ahead, please ask your question. Unmute and ask your question. Pratik, you just unmute and ask your question.
Thank you very much. Sir, I want to ask you that, sir, now just you explained us about the reaction of molybdenum oxide with fluorine, and we have considered fluorine as a nanoparticle. So can we use fluorine instead and try the same reactions?
Yeah, actually the fluorine, we can use a lot of fluorine for our nano surface, and that can be used for the catalyst for the nucleophilic substitution reactions. So that is still we not means like loaded fluorine items on the nano catalyst.
And sir, I want to ask that while explaining, you told us that aromatic reactions are not means there is no proper result we are getting for aromatic reaction, and we are trying. So can we try a combination of fluorine or any other halogen group, or can we use transition element or inner transition element as a nanoparticle if we can try a combination for getting over the aromatic reactions?
Yeah, that one possibility is that we have to modify the aromatic system with like a boron or some like a palladium iodine transition metal complex like tin aromatic system attached complex, and that we can use for the fluorination. That can be possible, but nano scale to synthesize such kind of nano aryl loaded nanocatalyst substrate, sorry, not the catalyst, substrate, it is very challenging to synthesize like a nano substrate.
Okay, sir. But sir, we can try it.
Yeah,
if possible.
yes. Yeah, there are a lot of reports. They use the like boron, tin, and that attached to the aromatic system, and then they treat with fluorine with some another transition metal like palladium, copper.
And sir, can we use radon or anything else like means which are highly nucleophilic in nature? Means we know that it participates in nuclear reaction at a greater speed.
Yeah, that not we have not think about that this rhodium like this much reactions metals, but we can see the possibility.
Okay, sir. Thank you very much.
Welcome.
Okay, any more question? participant can raise your hand, or you can just unmute and speak. Or you can also type your question in chat box. Okay, any question? Okay, if no question, let's thank Professor Sandeep Shinde for a very nice talk. Dr. Sandeep Shinde, thank you very much for giving very
thank you.
nice talk in the workshop. Thank you. Thank you very much.
Thank you very much.
Okay, we'll just go ahead and move with the next talk. We have with us Dr. Shivraj Karwar from Leuven, Netherlands. He has completed his PhD in 2015 from Material Science and Engineering, University of North Texas. Then he has completed earlier his MS from Material Science and Engineering from GPA. And then BTech from Department of Metallurgy and Material Science, College of Engineering, Pune. He was currently a guest researcher in Eindhoven University of Technology, Eindhoven, the Netherlands. Before that, he was a postdoctoral research associate in Eindhoven in the Netherlands from 2020 to 2021. From 2018 to 2020, he was a postdoctoral research associate in Friedrich Alexander University in England, Germany. Before that, from 2015 to 2018, he was a postdoctoral research associate at Delft University of Technology, Delft, Netherlands. Has graduated working as a graduate research assistant at United Texas, USA, from 2009 to 2015. Before that, 2014 to I think the same year, he was also working at Los Angeles National Laboratory, one of the biggest laboratory in America. Then he was also working as graduate research assistant in America, and has participated in many conferences and published many research papers in a high-profile journals. And now I request Dr. Shivraj to deliver a novel and efficient atomistic simulation method for thin film growth technology. Dr. Shivraj, you can start your presentation.
Okay, thank you. I hope you can see the presentation and hear me clearly.
Yes, we can see your presentation. You can see very nice background of your university.
Okay, yeah. Okay, sure. I would like to thank the organizers for organizing this workshop and also inviting me to present my work. So this is an ongoing work. I'm currently working as a researcher at Eindhoven University of Technology, and I would talk about the thin film deposition, simulations of thin film depositions, and I'm working with my postdoctoral supervisors here and also one of the postdoc at Eindhoven University of Technology in Mechanical Engineering Department. So this is the outline of my presentation. I will start with the motivation, research and motivation, and then I would give you a background of the literature, the existing simulation methodologies that are used for thin film deposition. Then in the next part, I will talk about the method, the novel method that we are proposing to simulate the thin film deposition, and I will end with the results and summary and outlook in this case. So the motivation for this work is the miniaturization of the ultrasound transducers. So ultrasound transducers are used for medical imaging purposes, as shown on the left-hand side here. And these ultrasound transducers have these multi-layer thin films. And although the specific application for this work is considered to be ultrasound transducers, but these multi-layer thin films are present in all the semiconductor devices that we use currently, like laptops, mobiles, and so on. So these thin films consist of very small thin film membranes, and at the atomic level, if you see, I have shown the model, like 20 nanometer thickness model of consisting of different atoms. So this multi-layer thin films consist of different materials, and these are manufactured using different experimental techniques such as PECVD, plasma enhanced chemical vapor deposition, sputtering, or atomic layer deposition, or physical vapor deposition. And they consist of different thin film membranes such as silicon nitride, aluminum neodymium, silicon, silica on the silicon substrate, and the total thickness of this free freestanding membranes is about 300 to 700 nanometers. So these freestanding membranes are these ones here, shown here. So the problem with this thin film membranes is that during deposition using experimental techniques, very high level of intrinsic residual stresses are developed. So when I say intrinsic residual stresses, these are developed when the deposition happens atom by atom. These are not externally applied stresses. And the magnitude of these stresses can be as high as 500 to 700 MPa. And when you consider the total dimension of these thin film membranes, 300 to 700 nanometers, this residual stresses, the intrinsic residual stresses will be very high. So this thin film, because of the presence of this very high intrinsic residual stresses, it affects the performance of this ultrasound transducers. It affects the frequency response, output pressure, and it could also lead to suboptimal performance or premature failure. So the aim of this present work is to establish the relationship between the thin film manufacturing processes and the residual stresses in the thin film stack. So as the deposition happens, as you deposit 5 nanometer, 10 nanometer up to 100 and 700 nanometer, how the residual stresses are developed in these thin film stacks. And to do this, to understand this, we are going to use the atomistic simulation models. So we are going to use these mathematical models to understand the deposition process and the development of the stresses. So there are some existing simulation methods available to do this. One of the method is the molecular dynamics, which is part of the atomistic simulation methods. But the problem with this molecular dynamics is that the deposition rates are very high. It is like 10 to the power 9 to 10 to the power 10 order higher than what is observed experimentally. So experimentally, when you use these deposition techniques, the deposition rate is, let's say, 1 nanometer per minute. But here, because of this very high deposition rate, there is not enough time for chemical reactions, and it could also lead to high porosity and amorphous deposition morphology. So on the left-hand side, I have shown one example from the literature. So this is basically a deposition of silicon, nitrogen, and hydrogen on the silicon substrate at 300 Kelvin. So I also tried to explore this just a little bit when I started this work. I also, just to replicate and also to understand myself. So you see here on the right hand side the free radicals of silane SiH4 and ammonia NH3. They are being deposited in this case. The radicals will be like SiH3, SiH2, NH2, NH, and so on. So these will be deposited at a very high deposition rate, and that is the problematic thing using the molecular dynamics simulation. The other method that is available is kinetic Monte Carlo, and in kinetic Monte Carlo, one needs the predefined deposition sites and reaction rates. So on the left hand side, what you see is an example from the literature, and here you would see that these silicon deposition on silicon happens on the predefined lattice positions. So in a way, this the positions of the atoms is fixed even before you start the simulation. So this is problematic because you are not allowing the deposition morphology to evolve from the simulations, but it is predetermined, and also one needs to have a complete catalog of the reaction rates and barriers and so on. And also the kinetic Monte Carlo will not allow you to calculate the residual stresses. So one needs to couple this with molecular dynamic simulations to calculate the stresses. So that is the problematic thing. Therefore, we are proposing, so this is an ongoing work and we hope to submit it very soon for publication. And at the heart of our method is the potential energy surface, which is shown here. And this potential, a two-dimensional potential energy surface is shown on the left-hand side. And one can see that this is the substrate, and this black atom is being deposited on this substrate. And this one, the top one, shows the potential energy surface, where there are these minimas, local minimas on the bottom, and then there are these transition states with the higher energy, and these are the barriers. So I will note this as B. So these are basically the barriers for the atomic movements, atomic diffusion, and the atoms to be deposited on the substrate. So when you consider the deposition of the atom, depending on the energy available at that particular temperature, this atom will be deposited at this local minimas, which are shown here, these local minimas, or at this global minima, shown here. There is a step here on the surface, and the energy for this atom to be deposited here is very less. When the atom is being deposited here, the atom is the energy is very less. Also, the barrier is very less. The barrier is very high in this case. So it depends on the energy available at the given temperature, at the given velocity for the atom to be deposited on the substrate. So this is just an introduction of the potential energy, and I will show you a three-dimensional surface of the potential energy and how we use this potential energy surface in our simulations in the coming slide. So in short, the novel method that we are proposing is called the minimum energy atomic deposition, or MEAD. So I will repeatedly use this short form MEAD in the coming slides. In short, the method can be described in two steps. The first step is to find the minimum energy position. So what I showed you here, the minimum energy positions can be either this local minima or the global minima shown here. That is the first step. And we have used two methods to do this. So I will describe these two methods soon. And once you find this minimum energy position, the second step in this process is to deposit the atoms randomly at this minimum energy position. So once you know this catalog of this minimum energy positions, you can just randomly place the atoms at this minimum energy position. So these are basically the two steps in this algorithm, the minimum energy atomic deposition algorithm. So, okay, so I will start with the first method to find the minimum energy position. So there are, I will talk about the two methods to find the minimum energy position. The second step here is common to both the methods. So the first method is to scan the surface to find the minimum energy position. So let's say you have a substrate here, silicon or any of the substrate that you want to use, and you equilibrate it at given temperature so that there are no stresses and during the simulation method. And so periodic boundary conditions are being used along X and Y. So Y direction is this along the right hand side, and perpendicular to the plane of paper, that is X direction, and the vertical direction is the Z direction. So free boundary conditions are used along vertical direction. It means that there is a surface here along the Z direction. So after you create or initialize the substrate, the next step is to place the atom to scan or probe. So I have placed one atom here, silicon atom on silicon substrate here. So this is just an example. When you are carrying out the actual simulations, you can use whatever elements that you want to use. Instead of silicon, one can use aluminum or whatever, silicon dioxide and so on. So here I have placed one silicon atom at the corner here, and two views are shown, the side view and the top view for the better visualization. Once you place the atoms, then I displace this atom along Y direction first, and then along X direction, and then repeat this process until the entire surface has been scanned. So you see here in the animation on the right hand side that the atom is basically being scanned on the entire surface. So I have used the displacement of the atom at each step as 0.1 angstrom, which is very small, so that the entire surface will be scanned, and we can know the energetics of the entire surface, like silicon atom on the silicon surface. So in this particular animation, I have shown the displacement after 1 angstrom, but otherwise the animation will be too long. But in actual simulations, when I carried out the energy calculations, I have displaced it by just 0.1 angstrom. Okay. After I have scanned the entire surface, you combine all these positions. So all these positions of only the blue atom. So here a top view is shown on the right hand side, and these are all the combined positions of this atom being scanned. There are no substrate atoms. The red atoms have been eliminated from this potential energy surface. So this is basically a top view of the potential energy surface. What I showed you before, a two-dimensional view, and I will also show you a three-dimensional view in the coming slides. So by combining all these positions after minimization, one can get this potential energy surface. And in this potential energy surface, one can identify these minimum energy positions shown by this blue circles or blue regions. And then there are these high energy areas, which are shown by this red color here. So, and this is the scale that varies, the potential energy varies from -2.6 to 0.7. So after identifying the minimum energy areas, the minimum energy locations, which are shown by these black circles here, some of these minimum energy areas are shown by the black circle. So we directly place the atoms at this minimum energy positions, and that constitutes one deposition iteration. So here I have shown the atom is being scanned on the surface, and one of the atom will be deposited here. So at one of the minimum energy areas, one atom is being deposited. Then the second atom comes in and it scans the entire surface, and then it will be deposited on the surface here. So you see here, the second atom is being deposited here. So this is the first atom, second atom, and now the third atom is being scanned. So the process goes on, repeats itself like this until the deposition happens. The problem with this method is that it is computationally inefficient, and only 3 atoms will be deposited in approximately 6 hours. So one can imagine that to deposit some realistic number of atoms, like 1,000 atoms, it would take forever. And if you consider one Avogadro number of 1 mole of atoms, it will be like 10 to the power 23 number of atoms. It will be very difficult using this this particular method. Therefore, we are not using that method. So I described you that method just to describe the research process, and also that was the initial method that we started with. But after we understood the problems in it, we came up with another method, and that I will describe now. So you have the initial substrate here, well equilibrated substrate. Again, a top view and a side view is shown here. 2 different views are shown here. Basically, this is the same simulation system, but in 2 different views. The second step will be to place the virtual atoms near the surface, so near the depositing surface here. So these virtual atoms are not interacting amongst each other, but they will be interacting with the substrate, substrate or the surface under deposition. So the pink atom that you see here, they are being deposited. They are the virtual atoms or the phantom atoms, and they are not interacting with each other. They will interact only with the substrate atom here. And once you place these atoms, the next step is to apply the random displacement. So this is not very important step, so I will go to next step. So once you place these virtual atoms, you calculate the energies. So one can calculate the energies of these atoms in single molecular static step or single molecular dynamic step. So it can be calculated in just few seconds. So once you have calculated the energies, the next step will be to remove the atoms with the high energy. So that basically what we are doing is we are keeping only the atoms with the low energy or the minimum energy, and therefore we call this method as minimum energy atomic deposition. So in this step, you are only seeing the atoms which out of these atoms, only the atoms with minimum energy are kept in the system, and all the other atoms are being removed. And these are the atoms in this 4th step. These are the atoms which are basically constitute in the deposition process. So once you have this, because these are the virtual atoms they are not interacting with each other, some of the atoms can be placed very close to each other, like what is shown here in these black circles. The distance between these atoms can be very low, like 0.5 angstrom, which is not realistic. We know that the atoms will be placed at least 1.5 to 2 angstrom away from each other when you consider silicon. So we remove one of the atom, and that is the next step, to remove one of the atoms from this the list of atoms which are too close to each other. And the final step will be to minimize the energy of the system. So you can see here that this particular atom is basically after minimization has not displaced much. And similarly, this particular atom also stays here because these are already placed at their minimum energy position. Therefore, during minimization, they are not displaced much. There will be small displacement because we are using a grid of atoms, and that grid of atoms doesn't necessarily find the positions exactly at the minimum energy positions. So just to summarize again, this is in the first method, we scan the entire surface, and on the left-hand side, a top view is shown. And here you can see a 3D view, a close-up of 3D view along this direction of this particular arrow here. So this is the 3D view here, and you can see the energy varies something like this. There are these high energy areas and then these low energy areas. This is the first method to scan the surface, and the second method, we have this grid of atoms, and here I have shown the grid of atoms colored by their atomic energy. So there will be some atoms, maybe not very clearly seen, but there are these atoms with blue color, which are the minimum energy atoms. And then there are these other atoms which have very high energies here. So let's say you have this, one of the atom with the lowest energy will be placed here in the method 1 on the when we place here. And the next step will be to minimize the energy of the simulation system. And then during the minimization of the energies, this atom, since it is not placed exactly at its minimum energy position, it will be displaced downwards, like downhill as per the potential energy surface, and it goes to its minimum energy position. So the position also changes, and also the color of the atom changes. So this big radius atom here, it changes its color from light blue to dark blue color. It indicates a change in this potential energies. So that is the second method. So this is basically the algorithm of this method. And just to summarize again, the algorithm and the steps shown in this minimum energy atomic deposition algorithm. So you start with the substrate one, then you can place the grid of atoms, apply some displacement. So the purpose of applying this displacement is that you are not probing the same positions every time. So random displacements are applied to these atoms, virtual atoms, and then the energies are calculated. After the energies are calculated, in the next step, you place only the atoms with the minimum energy and then minimize the energy of the system. When you minimize the energy of the system, some of the atoms will be displaced to their minimum energy position, which is shown by this small black arrow here. The next, okay. So what we are doing is, when we calculate this energy in this step here, we are calculating the unrelaxed energies. We are not doing any dynamics or static simulation. So these are just the unrelaxed energies given by the mathematical formulation like Lennard-Jones potential, or there can be different potentials which are shown by the Dr. Pawan Tripathi during the first presentation. So when we calculate this unrelaxed energies, you can see here on the left-hand side, the graph of the potential energy surface for the unrelaxed energies is shown here. And then we minimize. During minimization, you can see that the energies changes a little bit. There is little bit change in the energies, and also some small displacement up to 0.6 angstrom is observed. So this is anticipated that there will be some small displacement of the atoms because we are using a grid of atoms, and this grid of atoms cannot probe like literally every point on the surface like 0.1 angstrom away from each other. So we are using 0.7. When we use this grid here, we are using the distance between the atoms is like 0.5 or 0.7 angstrom. Otherwise, the number of atoms will be too high and it will be very difficult. The calculation becomes very slow. So therefore, we are using 0.5 angstrom and then let the minimization take over. So the minimization makes sure that the atoms are being displaced to their minimum energy position. So that is what we are doing here. So here I show you an example of aluminum deposition on silicon using this method. So you see the steps like a 25 by 25 nanometer substrate, silicon substrate is used. And the green atoms indicate basically the crystallinity in the aluminum deposited aluminum material, and the red atoms indicate the defects, which are like the stacking faults, also defined, also described by Dr. Pawan Tripathi in his first presentation. So basically, these red atoms are the defects in the aluminum crystal structure. So initially, you can see that the deposition morphology is amorphous. The gray atoms that you see here are the amorphous material, aluminum material at the interface of aluminum and silicon. And as the deposition thickness increases, the crystallinity increases. Here I show you an animation so that it becomes clear to you. Aluminum deposition on silicon here. So you see that how the deposition is happening. So in the previous slides, I showed you, when I showed you the algorithm, I described this method only for one deposition iteration. So you go on repeating this one iteration again and again, like 1,000 or 10,000 steps. And in reasonable computational time, you can deposit a large number of atoms, up to 5 million atoms and 100 nanometer thickness on reasonable computational time and computational resources as well. So that is the advantage of this method, that it allows depositing large number of atoms using reasonable computational resources. And yeah, so this is one example. The second example is aluminum deposition and aluminum. And here you can see this is the substrate on the left-hand side. And as the thin film is deposited, there is one defect that is being formed. And this defect is called a stacking fault. And you can also see several deposition mechanisms, like formation of these steps here. Then for formation of add atoms, formation of vacancies, and so on. So these are the mechanisms that evolved directly from this method, and they are not basically integrated when we do the simulations, like before we do the simulations. So this is the third example of silicon deposition on silicon, and silicon deposition on silicon results in amorphous morphology. So all these gray atoms that you see here, this is basically amorphous morphology, and the bottom blue colored atoms, they are the diamond crystal structure silicon. So yeah, this is the other example, and these are the animations of the same second and third example, aluminum deposition on aluminum and silicon deposition on silicon. So this is how the deposition happens. Yeah, these are the mechanisms and the defects that are formed. So here I show you in aluminum, on aluminum, you can see a stacking fault loop and the formation of terrace here, kink formation and kink propagation, step atoms, vacancies shown here, then atom cluster formation, and so on. In aluminum and silicon, you can see the defects like twin boundaries, stacking fault. And in silicon deposition on silicon, you can see this crystalline nuclei that are being formed in this case on silicon deposition and in silicon. So now this was our main aim when we started this work, to calculate the intrinsic residual stresses. And you can see here that after we have equilibrated the simulation system, and then we calculate the residual stresses. After depositing about 2.5 million atoms, we have calculated the residual stresses, and this work, calculation and analysis of the residual stresses, is in progress. And you can see that along the grain boundary and along the defects, the magnitude of the residual stresses is very high. And in bulk of the sample where there is high crystallinity, you can see that the residual stresses are very low. So this work, like the calculation and prediction of the residual stresses as the thin film is deposited, is under progress. And so I don't have much data on this thing right now. So to summarize, we have proposed a novel method, minimum energy atomic deposition, to surpass the limitations of the existing atomistic method. And in short, we scan the surface or probe the surface using two different methods for the minimum energy positions. Once you find this minimum energy position, you can deposit the atoms at these positions, and these are basically in two steps one can define this method. The assumption is that the atoms are being deposited when you say the minimum energy position. The assumption is that the atoms are being deposited at their equilibrium positions after long time evolution of the system. So in a way, we are only considering the final deposition place of the atoms. We are not considering the dynamics or kinetics of the atomic diffusion or propagation of the atoms, or when you place the atoms at certain angle and certain energy or velocity. So we are not considering all these things. We only consider the final deposition place of the atoms, and the outlook will be to calculate and predict the residual stresses in detail analysis of this thing. And then we also want to extend this method for the multi-elemental system. Currently we have used mono-elemental system like aluminum on silicon, aluminum silicon on silicon. We already have the idea. It is very easy to extend this method for multi-element like binary, ternary, and so on. Let's say you want to deposit silicon dioxide on silicon or silicon nitride on silicon. So that is the next step in this work. And I would like to thank you. And if you have any questions, I'd be happy to answer. Thank you again. I cannot hear anything.
If participants have any questions, they can raise the hand. And can you hear me? Can you hear me?
Yes, I can hear you.
Okay. Thanks.
Sir, I have one question.
Please go ahead and ask. Yes.
Sir, I have a question that we have used in this method as we have used aluminum deposition on silicon. Can in similar way we can use aluminum deposition on germanium metal?
Yes, you can. It is very easy to change this method, the algorithm. Instead of silicon, you can use germanium and carry out the simulation. Yes.
And sir, I have one more question that means I'm not sure, but as per the basic knowledge, is this method being developed by using a concept of N-type material formation? Because as we know, in N-type material formation also, we add an atom and we form a 5-electron structure. Means in similar way in MEAD method, we are also adding some kind of means we are adding an atom at local maxima, local minima, or the global minima. So is this idea been taken from that method?
No. This is a very generic method. So the basis of this method is the potential energy surface and where the atoms are being placed. So this is a generic, and it can be applied to any idea, even what you are saying, the N-type deposition of materials. That is the idea of this method, that it should be generic enough so that one can use broad range of materials and simulate broad
range. Sir, in future we can also try to make a combination of nano material with semiconductors also, or nano semiconductor, something of that kind.
Yes, that is the idea. Yes, that's correct.
So then, sir, while if we have to prepare some kind of such material, then we have to, means like we first in the first lecture, like sir explained us about the cryogenic temperature and the room temperature and all the conditions, other conditions. Then do we have to take any precaution for that, because we are using two complete different materials and trying to combine it to form a new nanoparticle?
Yes, so there is something called as interatomic potential. So if you are aware of this interatomic potentials like Lennard-Jones potential or embedded atom method potential, so you have to make sure that the interatomic potential that you are using replicates the basic properties like energies, surface energy, ground state energy, minimum energies, all these things. Once you make sure that these basic properties are replicated well enough, considering to the experiments, then you can carry out the simulations. Then the simulation results will be correct enough. If your interatomic potential is not good enough, then whatever result that you get will be wrong. So you have to be careful about the interatomic potential.
Okay, sir. Thank you very much, sir.
Yeah, thank you.
Okay.
Sir, Shiva sir, I have one question.
Yes, sure.
So thanks for very nice presentation. You have very nicely given the details of how So things are going on at atomic scale. So basically, I'm experimentalist, and I was very familiar with this atomic layer deposition and molecular beam epitaxy. So basically, these are the techniques which give a very high quality interface, and the growth mechanism is there. So how this technique is a different, MEAD technique is different than ALD and MBE based on the mechanism or growth mechanism or the experimental parameters.
Okay, so the difference is that when you use the experimental techniques, the atoms will be actually deposited, or the molecules or radicals will be deposited. There will be certain temperature and energy and the velocity of the atoms that they will be coming on the substrate or the surface under deposition. So in our method, we are not using all of that. We just directly place the atoms at the minimum energy position. So that is the assumption that atoms are actually, so in experimental, there will be some diffusion of the atoms, displacement of the atoms, or some reaction if you are considering the chemical vapor deposition. And out of that reaction, some final product will be formed. So that we are not considering, and that is the assumption in our method, that we place the atoms directly at the end. So yeah, that is the assumption. And also in terms of the growth mechanism, so we are making, the method is formulated in such a way that it should be able to give or propose the mechanisms observed experimentally, that the mechanisms are not intrinsically considered in the method, but they should evolve from the method. So instead of using in kinetic Monte Carlo, you have to know that there will be some diffusion of the atom even before you start the simulation. But in our method, we assume that this diffusion of the atom is evolving from this method, and also all the interactions and so on. So the mechanisms, I showed one example that there are these defects which are formed. Also the steps of the atoms are being formed, add atom vacancies and so on. So I think these are all the mechanisms which are observed experimentally, and these are evolving from our simulation method. And yeah, so we are happy that the method is able to show different mechanisms during simulation.
Okay, thank you. Thank you so much.
Thank you.
Okay. Any more question? Okay. If there is no question, let's thank Dr. Sivaraj for very nice presentation. Thank you, Dr. Sivaraj, for your presentation. Thank you very much. Thank you.
Thank you. Thank you for allowing me. Thank you.
Yeah. Now I hand over the stage to Dr. Suraj Jejurikar. Professor Jejurikar, are you there? Professor Jejurikar, can you hear me? If you are hearing me, just unmute. I think you are there in the meeting. You just unmute and start to speak. Okay, I think there is still some problem with network issue at his end. I will just introduce the next speaker. We have next speaker already with us. We have Dr. Kirti Rathi. She is currently working in a Jeong National University, South Korea. Prior to this, she has completed her PhD from IIT Roorkee in the specialization of nanotechnology and MTech degree in nanotechnology from DC RUST, Mural, Haryana. Dr. Rathi had worked at a Wayne State University, Wayne State, Detroit, Michigan, under Indo-US Joint Center for Nanoscale Research Program funded by again Indo-US Science and Technology. First in esteemed international journal, and one Indian patent as well. Dr. Rathi had attended many conferences. Her research expertise in the synthesis of nanomaterials, analyze their optoelectronic properties and sensor technology. Now I request Dr. Kirti Rathi to give her presentation. You can, Dr. Kirti, you can share your screen.
Yes, yes. Okay. Thank you, Professor. I'm sharing my screen now.
Yeah.
Yes, your screen is visible, Kirti.
Hello, everyone. I'm Dr. Kirti Rathi, postdoctoral researcher in Gyeongsang National University, South Korea. Here I'm going to present about the nanomaterials-based sensor technology. Here I'm going to explain about the nanomaterials, their properties, what are the sensors, types of sensors, and material selection, like how we select the nanomaterials for particular sensing application. Fabrication of sensors, like basically gas sensor, humidity sensor, and pressure sensor, and the summary. Here I'm talking first of all, what are nanomaterials? Nanomaterials are in nanoscales around less than 100, at least one dimension should be less than 100 nanometer. And there are some types of nanomaterials, which is basically depends on the number of dimension, like 0 dimensional, 1 dimensional, 2 dimensional. In case of zero dimensional, all dimension at nanos are at nanoscale, like quantum dot. If we talk about the 2 dimensional, here the 2 dimensions are at nanoscale and other dimension is not. For example, nanowire, nanorods, carbon CNTs, etc. If we talk about the 1-dimensional nanomaterials, in this case, the 1 dimension at nanoscale and other 2 dimension are not. For example, any coatings and film fabrication. And if we talk about 3 dimension, in this case, there is no dimension at nanoscale, like composite thick film, if we talk about that one. So there are some types of nanomaterials like graphene, examples like graphene, CNT, MXene, quantum dot, polymeric nanomaterials. Now, why do materials at the nanoscale have different properties? Because when the size of the particle reduced, its surface area to volume ratio increases, and which can lead to greater chemical reactivity and affect their mechanical strength, hardness, formability, and toughness. And size of grain also control the electrical properties, optical properties, and chemical and magnetic properties. So that's why the nanomaterials are used in various applications like sensing applications, some supercapacitor, lithium-ion batteries, fuel cells, etc. Now, why the nanomaterials are used for particularly sensing application? What are the criteria for choosing the materials? So the reduction in size of the sensing part is important in order to better miniaturize the device. Another parameter is the reduction in power consumption. Third is the increase in sensitivity because of the good electrical properties, as well as high surface area to volume ratio and direct detection. Why we choose, how we choose the material for particular application, that depends on which type of application we want to, in which type of application we are going to use the material. So that depends on the manufacturing process, type of material and their properties and the geometry. Now we talk about the sensor. Sensor is nothing but it's a technological device that detect or sense a signal, physical condition, or chemical compounds, like in voltage, in terms of voltage, resistance, or frequency. Sensor, it's a gateway between the physical and digital world. There are various types of sensors to solve some problem of electronic devices like gas sensor, touch sensor, light sensor, humidity sensor, etc. Now, I'm going to explain why, how we choose the material for particular sensing application. For example, for temperature sensor, material should be in wide temperature range, have excellent repeatability, stability, and resistant to chemical and corrosion. For example, platinum, copper, nickel, and nickel iron alloys. Another is mechanical sensor. In case of mechanical sensor, material should be mechanically stable, super elastic, resistant to corrosion, and electrically conductive. For example, graphene, CNT, and piezoresistive materials. Other is chemical sensor like gas and humidity. In this case, electronic properties of the material should be good, high surface area to volume ratio, highly chemically reactive. And if we talk about the humidity sensor, so material should be hydrophilic in nature, not in hydrophobic, because we have to measure the humidity. If we talk about the optical sensor or photodetector or light sensor, so material should be light sensitive material, optical property should be good, and resistance to chemical and corrosion. For example, cadmium sulfide and lead sulfide. For biological sensor, material should have a high electrical conductivity, nanoscale size, and most importantly, non-toxic, because here we are using the sensor as in bio application. Now, I'm focusing on the gas sensor. Basically, the gas sensor is a device to detect the concentration of analyte gases into an electrical signal. There are various types of gas sensing gas sensors, like, and basically it depends on the sensing mode, like resistive type sensor, capacitive type sensor, IR sensor, wavelet sensor, etc. Here I'm going to explain about the chemi-resistive type sensor. Now, what is the chemi-resistive type sensor? Chemi-resistive type sensor is a sensor where when we pause the gas onto the sensor, its resistance will vary. So that is called the chemi-resistive sensor. Here, the sensor response can be defined as del R by R in percentage, Rg minus Ra divided by Ra into 100. Here, Rg is the sensor resistance in the target analytes, and Ra is sensor resistance in dry air. This is the experimental setup or a how we fabricate the sensor. So we use generally the ID. Onto the ID, the material is drop casted or spray pyrolysis or spin coater, and then it is connected with the electrode with power supply and digital picoammeter, and it is placed inside the chamber where the gas is presented. And after causing different ppm amount of gas, its resistance will vary. Now, this is the example of chemi-resistive type sensor. This is wireless handheld device based on polylactic acid protected, highly stable CTAP functionalized phosphorine for carbon dioxide gas sensing application. Because first of all, there are some drawbacks in the chemi-resistive type sensor. Mainly, it is not effective. It is not good in humidity, different humidity. So we try to protect with the humidity by using the polylactic acid membrane. So this is the preparation of phosphorine sensor. Here we use the black phosphorus, and we did sonication in the presence of the NMP for 8 hours. So phosphorine is presented, but after, if we check the stability purpose, the pure phosphorine is highly degraded in the environment, so it degrades very fast. So to reduce the degradation rate, to enhance the stability, here we added the CTAB. We did the functionalization by the CTAB so that we can enhance the stability. And here we are using, we try to make one handheld device by using the PTFE box. In the PTFE box, we use Arduino and the Bluetooth device, and here we connect, here we put the sensor, and we cover the sensor with the polylactic acid membrane. These are the sensing response. When your sensor is passed into the carbon dioxide gas with different concentration, its resistance start increasing. It shows that because the CO2 gas is reducing as a reducing agent, and the PC tab behaves like a P-type material, so its resistance starts increasing when we increase the concentration of the carbon dioxide gas. So this is the response and recovery time at 500 ppm with different PC tab and with PC tab with protected with PLA. So here it is clearly observed that the response after protection with PLA or before PC tab, there is no that much change in the response. It is much similar. And in case of response and recovery time also, but the problem is humidity effect. When we use the PC tab without any PLA, so and we put into the different humidity environment, so its sensing response vary at constant ppm of CO2. But in case of polylactic acid PC tab, there is no change in sensing response in different humidity sensor in humidity environment. This is just because of the PLA membrane, because PLA membrane restrict the interaction of the PC tab surface with the humidity. This is the this is the sensitivity. Sensitivity is nothing but the correlation between the sensing response and the different gas concentration. Here the sensitivity is the 0.03563 per ppm in case of PC tab, and in case of PC tab with PLA, it is 0.03291, which is much more similar, but it is less. This is just because of the PLA, because when we protect the PLA, so some CO2 gas may not enter inside the inside the chamber just because of the inside the sensor just because of the PLA membrane. So that's why its sensitivity a little bit decreases, but its limit of detection increases, its correlation coefficient also increases, and its stability is almost similar after 30 days. It is 99.5% after 30 days. Another is the humidity sensor. In humidity sensor is the humidity measurement determines the amount of water vapor present in gas that or a mixture such as air or pure gas. There are two types of humidity sensor, capacitive type or resistive type humidity sensor. I focus on here only resistive type humidity sensor. It measures the electrical resistance change, which usually inversely proportional to the relative humidity. What are the main background problems in case of resistive type humidity sensor and the capacitive types of humidity sensor? In case of capacitive type of humidity sensor, the cost is high, have a limited signal circularity. And in case of resistive type humidity sensor, when we expose to the sensor into the chemical vapor, it may contaminate because of premature failure. Another is the value may shift when water soluble coating are used. I already told material should be hydrophobic if we use for particular gas sensing application, or we have to protect with some other material to the environment. This is the example of resistive type humidity sensor. Here, the impact of doping on GEO, fast response and recovery humidity sensor. Why here we choose the graphene oxide? First of all, graphene oxide is highly hydrophilic in nature. It is conducting. It is it has high surface area to volume ratio. This is the sensor fabrication and experimental setup. This is the experimental setup, but that is the customized one. Here we drop cast onto the glass substrate, which is connected with the copper sheet, and we drop cast different samples, graphene oxide, boron doped graphene oxide, and lithium doped graphene oxide. Here we created the different humidities by different salts and different conditions. Lithium chloride, magnesium chloride, calcium chloride, etc. This is the linearity and sensitivity curve of graphene oxide, lithium doped graphene oxide, and boron doped graphene oxide. here it is clearly observed that the lithium doped graphene oxide is much more linear as compared to the undoped graphene oxide and boron doped graphene oxide. This is because when we do the doping, so lithium intercalate lithium helps to enhance the high surface area to volume ratio, as well as it it plays in the interstitial side of the graphene oxide layer. This is the response and recovery time. In case of response and recovery time, the lithium doped graphene oxide having very less response and recovery time, around 4-second response time, and recovery time is around 25 seconds, which is comparatively good with boron doped and undoped graphene oxide. If we talk about the hysteresis loss, that is also very important when we do the 0 to 100% of relative humidity, and we back to the 100 to 0% relative humidity. So there should not be any loss. It should follow the same path that is good for commercialized purpose. So in case of lithium doped graphene oxide, it shows very less hysteresis loss. It shows around 0.83% hysteresis loss, which is very less as compared to boron doped and undoped GO. This is the proposed mechanism, like how electrical resistance increases when under different humidity condition. The electrical response of the sensing material to humidity is generally related to the physi-adsorption of water molecule. At a low pH, the water molecules are attached with the double hydrogen bonding, and maybe they restrict the motion of the water mobility of the water molecules. But as relative humidity increases, water molecules are physisorbed by the single bonding of the hydrogen bond, so which creates the hydronium ions as a charge carrier. So resistance starts decreasing as relative humidity increases. Now another is the piezoresistive pressure sensor. Here, for piezoresistive pressure sensor, generally for pressure sensor, we need material should be flexible, should be mechanically stable, and good elastic property. So for that, here we perform basic bridge analysis, especially find out the voltage as a function of input voltage and various resistance. Here, the sensitivity is calculated by del R by R0 divided by pressure, change in the pressure. This is the example of chemi-resistive sensor, super compressible and mechanically stable graphene aerogel for flexible pressure sensor. Here we use the graphene aerogel. Why? Because graphene aerogel is highly flexible, which is preferable for wearable devices and having a good electrical conductivity. So this is the synthesis of graphene oxide. Graphene oxide is synthesized by different reducing agent to enhance the different cross-linking, because if we need a good mechanical stability or good chemical cross-linking, so for that we have to focus on different reducing agents on the basis of pH variation. And after reduction at 40-degree temperature, hydrothermal, I did hydrothermal at 160° for 3 hours, and then freeze drying for at -60° for 4 hours, and vacuum drying for 48 hours. So they are different aerogel is formed. This is the mechanical properties of graphene aerogel. This is mechanical testing device in which we put we vary the different load, and we check the compression decompression. And this is the recovery test from 10 to 80% of strain, and it is clearly observed when we do the reduction with the help of hydrazine hydrate, its recovery is almost about 90% at 80% of strain. This is because hydrazine hydrate reduction having pH around 10, that is basic pH. When we reduce the material, it creates ionic interaction, and that is very useful for because ionic interaction and hydrogen bonding have a self-healing property. So when we compress the material, after decompression, it regains their own shape. This is the cyclic test at constant stress. In this case, the cyclic stress is constant. The normalized stress is around 99% after 1000 cycle and 20th cycle. It is same, but it is less in case of RGO, RGO ascorbic acid, and RGO urea. That's why for sensing application, RGO-HH aerogel is much more suitable than other. This is the sensor fabrication and sensing mechanism. Here, we fabricate the sensor. We use the aerogel. We coat with the conducting tape and silver paste to make the proper connection. And then we put into the mechanical testing machine. We connect with the data acquisition system. And when we compress that one, its resistance start decreasing, because aerogel have high porosity. When it compresses, so pore size start decreasing, conducting path increasing, automatically resistance start decreasing. So here we try 5 cycles, 5 times for different strain, 10% strain, 30% strain, 50% strain, and 70% of strain. And it shows good sensitivity, which compared to other literature survey, which shows 5.7 kilo per kilopascal. So this is my summary. Here, my main motive is to explain that the criteria, the selection of materials or nanomaterials, why they are important. Nanomaterials are important just because when we reduce the size, its chemistry and its physics totally change because it depends on the size, and which is beneficial for smart application. Second, like selection of the nanomaterials according to the application are very important. Third is reduction in the size of the sensing part or the transducer in sensor is important in order to better miniaturize the devices. Sensitivity can increase due to the better electrical properties, and which depends on the nanomaterial size, limit of detection, and can be lower very small quantity for sample can be analyzed. Thank you very much. Please feel free to ask any question. I'm happy to give you the answer.
Am I audible, Dr. Kirti?
Yes, yes.
Yeah, thank you very much for your wonderful talk. I'm Dr. Suhas Jazurikar, the chairman of this for the particular session. As you said that the talk of your title, the title of your talk was nanomaterial based sensor technology, and I must say that it is really very much informative. Throughout the talk, you not only discussed about the sensor technology, but you also showcased us how to fabricate them, right? And more on that today, how the nanomaterials can be implemented to make these kind of sensors, and how to miniaturize these sensors, as well as how to embed them with your mobile phones, right? So it was very wonderful talk, and I'm pretty sure that our audience will also, audience must have liked the talk. And now I would like from audience some questions to be asked with Dr. Kirti. The session is open for question and answer. Pratiksha is there who would like to answer, who would like to ask. Pratiksha?
Yes, sir. Thank you, sir, for
Please,
giving me a
proceed.
chance to speak. Ma'am, as you know, this program was of 2 days, and for my poster preparation, I was studying about the concept regarding to carbon nanotube sensors, which we use for the controlling and sensing of a brain. In that method, ma'am, I studied while making that poster, I just studied that we are using a combination of carbon allotrope, fluorine and graphene together, and we are making a tube from that, which is of SWNT, MWNT, and CD quantum dots, and it has been used in brain so that it has been connected to the cortex, and by the neurons, all the data is being collected and is being sensed. So I had a question, ma'am. Can we make a same nanotube with platinum and gold combination and use it? Because I know, ma'am, it's costly, But will it be
Yeah.
effective more way?
Yeah, it will be effective. If you use the gold, I think that is much better than platinum for biomedical application. And another thing is that when we make any sensor or any film on that, so still gold and silver particles help to make a much more uniform film, and also it is not harmful for our like biomedical application. So I think silver and gold is much better than platinum.
Okay, ma'am, because ma'am, platinum also doesn't affect a lot on body means because I have studied and read upon it. So I asked you this question. And ma'am, other thing that you told us about the aerogels, in similar way, can we use silica gel also? Because silicon is also used as a nanoparticle in most of the materials. So can we try any combination with any other element with silica and form gel, and which can be used for different nanoparticle experiment?
Okay, why you are using silica? Like, is there any particular application? Because if we use silica for any piezoresistive properties, though silica is not suitable, I think, because for that we need some good electrical conductivity as well. So, like, actually, why you basically want to use silica? I feel like if you want to use if you need some flexibility, so you can use hexagonal boron nitride. That is much better if you enhance the flexibility. And if you want to enhance more, like nowadays, I'm trying to focus on to make a self-healable flexible aerogel by using the silver particles, because silver particles with some other surfactants which may enhance the more physical cross-linking. By that we can enhance the more self-healable aerogels, which is very suitable for the sensing application or other application like jackets if we need, or some any thermal insulating like TIM materials, if thermal interface materials we can use. So I'm asking, like, why you want you use silica as an aerogel? Why? Like, is there any particular application?
Sir, ma'am, just I wanted to ask this question because we can use for any chemical biosubstance development for that way. Ma'am, I'm just a SYBSc student, so I also don't have a complete knowledge, but had an idea and has been reading about some topics related nanophysics, so I just asked this question.
Okay. So silica you can use with polymer, any polymer which has PG you can try with silica, but without any application, like I'm not sure like why you want, because silica is very good aerogel, no doubt. It has a good thermal interface material property, and it is using in so many applications. So that's why, as I told you, like when we prepare any material, so our main motive, like why we prepare this material for, is there any application, or why we try, which type of property we want to enhance. So that is very important. If you want to know, or if you want to ask anything, you can.
Pratiksha, hope Dr. Kirti has answered your questions. And this is really very encouraging that the SYBSc student is taking a lead and asking some questions at the international conference. I'm very much, this is very much appreciated, Pratiksha, and keep it up. If someone else would like to answer some questions to Dr. Kirti, please raise their hand so that we can unmute them.
Sir, I have one question. So
yeah, please. Arif, please.
Yeah, thank you, sir. So, Dr. Kirti, thank you very much for your nice presentation. As you've seen that even SYBSc students are encouraged by your work. So that's as Dr. Suhas sir says, that's a very nice to know that students are taking lead in the research. My question is very fundamental, belong to your piezo-resistive sensor. So most of us are very well known regarding piezoelectric sensor, basically who sense the pressure. So as compared to this regular piezoelectric material, this aerogel-based, graphene-based aerogel material, how the performance, if you compare, can you say some about it?
Can you tell? Pardon me, I didn't get what you asked. Can you repeat it again, please?
Yes, sure. So
Yeah.
basically, this question is belongs to second part of your presentation, where you have shown graphene aerogel based piezo resistive sensor, right?
Right.
Right. So in general, there are piezoelectric materials
Mhm.
where the pressure is converted into electrical signals.
Yeah,
Like,
electric energy, right.
right, electrical energy. So if compared to those sensors, these aerogel based materials performance,
Mhm.
which is better if we compare?
Uh, if we compare with piezoelectric, then piezoresistive, I think piezoelectric is still good than piezoresistive. And if we talk about the aerogel, because as we know, when we prepare the aerogel, so automatically its conductivity start decreasing just because of the porosity increases. So but the main thing in the piezoresistive flexible sensor, your mechanical stability is enhanced, and you can use it any flexible or wearable functional devices. That is very much easy to use that one.
Right. Yeah. Thank
Yeah.
you so much.
Okay. Thank you, Professor. Thank you.
Thank you, Arif. Thank you, Dr. Kirti. If someone else is interested to ask some questions to Dr. Kirti, please raise their hand, because the discussion is really very going on a very good note, and a lot of participants can get a lot of information from Dr. Kirti. I'm pretty sure about it. Please raise their hands. Okay. So it looks like that there are no more questions from the audience side. So I would like to take privilege to thank Dr. Kirti on behalf of Amity University, Professor Dattatray Latte, and the audience to give this nice talk for the today. Thank you very much, Dr. Kirti. Thanks a lot.
Thank you, Dr. Latte.
Thank you. Professor Latte, I would like to apologize for joining this conference a little bit late, and I'm pretty sure that all the lectures look like very intense as well as very informative. So with your kind permission, shall I call our next speaker of the day?
Yes.
Yeah.
Yes.
So I would,
ahead,
yeah.
please.
So I'm very
Thank you.
happy to call Dr. Krishna Pawar from Hanyang University, South Korea. His topic for the discussion is an introduction to the new age of nanosensors. Dr. Pawar is research professor from the Research Institute of Industrial Science, Division of Material Science and Engineering, Hanyang University, Seoul. He has completed his master's and PhD from Department of Physics, Shivaji University, Kolhapur, and he is having more than 7 years of research as well as teaching experience. He is a reviewer for 5 international publications, as well as he has published more than 20 international journals. He has also published one book, and I'm very happy to call Dr. Krishna Pawar to deliver his talk. Please, Krishna Pawar, the stage is yours. Thank you. Dr. Krishna.
Can you hear me, Swaz? Okay, maybe I think he's taking slightly more time to join. Maybe I will share some of my presentation meanwhile. Let me know if you can share my slide. Can you share my presentation? Can you see my presentation? Okay.
Yes, sir.
Okay, so I will talk on these novel 2D materials, again, some of the synthesis of this 2D nanomaterials, their properties and application. So let me thank the funding agency generously support my research since quite long time. Let me thank my collaborator, Professor Suhas Jazulkar, already here as a chairperson, and a lot more collaborator from India as well as abroad. So I am here editor board of these 2 journals, AIP advances, the impact factor is increased actually 1.6. This is, I think, some 3-4 months back presentation. There is another journal that is Royal Society Open Science, whose impact factor is 2.51, but it's now changed to 3.6. There are 2 more journals from IOP Electronic Structure and IOP Synod. So there are also good scientific journals to publish your research related to material science, engineering, chemistry, physics. It's a kind of multidisciplinary open access journal. And the journal is also open to submit your original research paper as well as review article. And currently there is no open access fee. You are feel free to submit your research paper in these journals. So this brief outline of my talk. So first part I will have talk on synthesis, properties related to graphene and graphene-like materials. Second part, graphene-like other layer materials, and third part, what happens if we can combine these 2 materials like graphene and 2D inorganic layer materials. And of course, the last part will be there is another rising material of 2D MXGene for novel device technology. Can be combination of various carbides, nitrides, and carbonitrides finally to make the kind of devices which is required for the hi-fi technological applications. And finally, the conclusion. Okay, so these are some of the facilities we have in our laboratory. We have optical microscope, we have chemical vapor deposition, we have gas analysis system, we have benchtop photolithography system, we have stencil mass for patterning of the devices, we have potential state, galon state for making the kind of application based on supercapacitor and battery. Also have this electrical characterization system for characterization of gas analysis, including various gases, including we are especially working on NO2 sensing, ammonia sensing at room temperature, as well as alcohol sensing and humidity sensing at room temperature. So the coming future is of flexible devices. So we're also working on low cost sensor, again based on nanomaterials. So sensors should be self-powered, they should be flexible, and they should be wearable. Then only then we can use it for the technological application. And cost for intended environment, if you consider the cost of the sensor should be as low as, so that everyone can afford the type of the sensor or the kind of applications. The sensor which I have shown here is application for to detect cardiovascular disease. That is very important kind of sensor which is needed for the technological application. Okay, so for example, the remote monitoring of health is also important. You know, during the COVID, we have found that because we're not able to go anywhere because of the COVID situation since last 2 years, and the remote monitoring of health becomes very, very important. That heart rate, for example, rate and the respiratory system of the material, for example, kind of application of location, GPS, communication gateway. These are the example how person can be continuously monitored if he has wearable devices. For example, something happened to this person, he can immediately be connected via internet or Bluetooth. He'll be same time he'll be informed to his family or his doctor, as well as emergency vehicle will come and he will pick up the person and admit to hospital. By the time he has all the variable sensors, and these sensors will give you all the data, including temperature, pulse rate, everything, blood pressure, and all these things. Data will be there. It will help doctor to give the proper treatment immediately, so that life of the person can be saved. So this is another project which we are working on. In another 10 years, you know, the smart car, already the flying car, we're talking about flying car and all these things, but this car will be a smart car. Basically, Google have already developed a driverless car. Basically, if you want a driverless car, just imagine a driver with a car without driver, right? And basically, it's very much possible. And already there are cars in the USA to map all the roads and everything. There's already Google has been done a lot of work in this particular area, and we're working on fire sensor. So these are the kind of sensor. If you want to drive a car with the driverless, so these are the number of sensor which is needed. And currently, what we are facing the challenges of again, the materials is very important. Basically, nanomaterials. Why nanomaterials? Because of high reactivity, high sensitivity, high selectivity. So these materials are ideally suitable for integration, signal processing, fabrication, and basically finally, because so small, right? Devices should be so small. So packaging and all these things are also very important. We're also working on 2D nanomaterials for various kinds of applications. There are applications including hydrogen generation, nanomaterial processing, batteries, energy storage, supercapacitor, fuel cells, materials for coating technology, conductive technology, and all other. So basically, graphene is a monolayer of sp2 bonded carbon atoms, which is known as the mother of all graphitic forms. Just imagine a graphene sheet. Just imagine a benzene ring, which is connected in a state like paper, right? Just so, what is the advantage of this graphene? Just imagine, because this is the mother of all graphitic. Just you can fold to get the zero-dimensional buckyball. You can roll the graphene sheet to get the one-dimensional carbon nanotubes. And same time, you can put one sheet each other to get the three-dimensional bulk graphite material. So it is used as a starting point of calculation of all these various forms of carbon-based materials. So it is studied since last 60, 70 years. And at the beginning, when 1910, 20, there are some papers of synthesis of graphite oxide. So still synthesis was really challenging. But this challenge was taken by these two scientists, A.K. Gaim and also who received Nobel Prize in a very short time because of the high performance of this particular material and basically technological applications. So why graphene? Why people are talking about graphene? Because it is the thinnest object of the wherever obtained. The thickness of one layer of graphene is just 0.34 nanometer. When you talk about the strength of this material, it is 200 times stronger than the steel. And at the same time, it is flexible, it is stretchable, and a very important part, it is transparent. You just imagine a material which is so thin, which is 200 times stronger than steel, and which is also a transparent material. And to talk about the electronic properties, it is highly conducting material. Therefore, it can be used in a transistor. Also, there is another application of impermeable to any molecules. So it can be used to store any kind of gas. And high specific area, surface area of this graphene is so high. So that is also advantage. So that is advantage of having surface area. A lot of these kinetic reactions, catalytic reaction, the rate of reaction can be faster when we have very high surface area. Again, this graphite is very highly stable structure. Again, graphite is easily available and can be a low-cost material. Here I am showing you a pencil. If you write anything on the pencil, this is actually a multi-layer of graphene, graphitic layers. As number of layers are more than say thousands. So whatever we're writing on the paper is actually 10, maybe more than 1,000 layers. So this still as a graphite. So if it is layers, number of layers are less than 10, then we can say this is a graphene. Because wherever writing, we are actually writing graphene layers. So we can't call this as a graphene because number of layers are very high. So this is whatever writing on paper is still a graphite layers. But it is possible to have monolayer of graphene on this paper also with some experimental analysis. Okay, so why graphene is so important? Because when you talk about the graphene, this is energy of electrons. This is physics people are very much attracted to, where energy of electrons is directly dependent on the wave vector. Or in another way, it shows very high conductivity. Direct solid, the conduction band and valence band in semiconductor, normally there is a gap. In insulator, there is a slightly more gap than the semiconductor. In insulator, there is a more gap than the semiconductor. But here it is a direct band gap, and also the band gap, there is no band gap. So the conduction band and valence band, they are just touching each other. So this is the kind of example of semi-metal. Metal, we say conduction band and valence band, they are overlapping. In semiconductor, there is a slight gap, but here conduction band and valence band, they are just touching each other. So this brings very unusual physics and chemistry. So therefore, it is a very direct solid black transport of carriers in many others. For example, this is an example of field effect transistor. when you apply negative gate voltage or positive gate voltage, still we have charge carriers in your channel, and this gives unusual physics properties of the material. For example, I have this very simple standard equation of energy, momentum, and mass. So, for example, charge particle which have some mass, right? E square is equal to m square c raised to 4 plus p square c square. So, when here in graphene, when you apply some electric field, right? So, electron travel in this particular graphene sheet with so high velocity, because whenever we're moving with so high velocity, sometimes you view as a massless particle. Actual electron has mass. So suppose because of the velocity, it views as a massless particle. So m is equal to 0 here. Energy of electron with which electron is traveling in a graphene sheet is directly proportional to 1/300 times the velocity of light, which is very fast. Therefore, electron in graphene behave as if they are actually massless. But actually, electron has mass. So this brings a lot of challenges as well as a lot of advantages as a kind of applications. So how to make a graphene basically? So there are a number of ways, physics, chemistry, ways to make this particular graphene. So this is a very simple method. You need a graphite crystal, you need a Scotch tape, which is available in the market with 10 rupees cost. And then we need a kind of SiO2 substrate having 300 nanometer thickness, or any kind of thickness is fine, but 300 nanometer I have choose as SiO2 thickness because it gives very good contrast for single layer, few layer, and multi-layer of graphene, so that I can identify this under optical microscope. So what you want to take, we need this high quality graphite crystal, I need this Scotch tape, which is available in the market. Then I need SiO2, Si substrate, and then I need a simple optical microscope, which is available in any school, college, laboratory, where I can see actually this SiO2 substrate under this optical microscope, and I see what is the color contrast of that particular layers. So what you want to do, you take this HOPG, you take this Scotch tape, you put that Scotch tape on the graphite crystal, you put slight pressure on it, and then you can take out this single or few layer of graphene, and then you just go to optical microscope and see if you can actually see the color contrast based on this particular thing. So, and then of course you can do the characterization, other characterization like AFM and TM and all other things, but optical microscope with the color contrast itself, you can identify whether the deposited, the layers, a single layer, bi-layer, or multi-layer kind of thing. Okay, so there is, you can just identify just this another optical image. See, the one layer of graphene with thickness is 0.30, is very light in color, and there is another few layer, this 2 layer of, then 3 layer, and this of course the blue part which we see, that is actually multi-layer in nature. And of course, so there is a with very small kind of chemistry, how we can synthesize this particular few layer of graphene or single layer of graphene. You take graphite powder and you do oxidation in presence of very strong acids, and you will get the graphite oxide, and you can do ultrasonication by just mechanical explosion. You can do thermal explosion by heating the sample at high temperature. Of course, you will get single this graphene oxide layer. Of course, you have to reduce it by using some reducing agent like hydrogen, and you will get the single layer of graphene. And so this is of course in a solution form, and you can of course deposit on any kind of substrate for application or any kind of characterization method.
Hello.
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 Yes,
Hello.
yes.
Hello.
Yes, we can hear you. Yes.
Can you hear me, Dattatreya sir?
Yeah, we can hear you. Yes.
Okay. Sorry for the trouble. It was great trouble.
Okay.
But
Arif,
I think
is PPT are ready?
yes. I am also presenting. I am
Okay.
only presenting my PPT.
Okay. Okay. I will stop my presentation and I will give a presentation on some other time. Thank you. Thank you. Yes.
Dattatreya sir, thank you very much because there is a technical problem. you started a lecture, because we have audience like from BSc and MSc and all type of faculties, and this time is utilized by Dr. Dattatraya Latte sir lecture. So thank you, sir. Thank you for, in the meanwhile, you in a tight schedule, you just explain your very nice presentation. Thank you, sir.
Okay, Krishna, please go ahead.
Yeah, you can go ahead, Dr.
Please restrict your lecture now to 20 minutes. Because
Yes.
Share your screen, Dr. Krishna.
Yes. Okay, can you see this?
Yes. Your screen is visible.
Thank you. Okay, my voice is good. Okay.
Yes. Go ahead now. Yes. Make
Yes.
up in the presentation mode. And you can
Yeah.
go.
Yeah, I'm doing. So good morning. Good morning, all of you. I am Dr. Krishna Pawar, research professor, the Research Institute of Industrial Science, Division of Material Science and Engineering, Hanyang University, Seoul, South Korea. Okay, I'm working in Hanyang University in Samsung project under the guidance of my two professors. Those are Hyunwoo Kim and Sang-Sup Kim. They are the oldest people of sensors in South Korea. Okay, so we are having oldest sensor lab in South Korea. So as Kirti ma'am told us about the sensor, I will just quick review the what is sensor and all those things. So sensor is any device that will give us output by means of any physical, chemical or biological change. So the natural sensors are our body parts, our nose, our eyes, our skin. Okay, so these are the natural sensors, and these sensor at the right hand you can see the remote control, mobile, your watches, and Siri. Now Amazon has developed this sensor. So these all new sensors are based on different kinds of strategic sensors. Those are physical, biological or chemical. So the sensors are most importantly used for the five things. Okay, first is the measurement, any change in an atmosphere in or your body or something, any change is there, then for the measurement of change we need sensor. Also by using sensor you can get the energy and you can transfer it, or you can recognize it, or you can measure it. Then third type is we are using sensors for signal recognition and convergence. So if we are having any kind of signals that we have to recognize, that we have in order format, in different format, we need sensors, or any conversion also we need sensors. And the most important part nowadays we are having is the control and monitor. So the controlling and monitoring all the data, atmosphere, our body issues, health, all we need is the sensor. So the oldest sensor we know we are having is this, and this sensor is knowing for earthquake sensor. So this is the oldest sensor we are having. However, we don't know who built this. Okay, so we are having only one person. We know the first person who built the sensor, that is Warren Johnson. He has invented electrical thermostat with the thermometer in 1883. So the known person of sensor who has developed sensor, patented it, and gives proper mechanism is what, who is, okay, this is Warren Johnson. So we are having different kinds of sensors. These sensors are based on their interaction with the analyte. Okay, the analyte is the thing which we want to sense. Okay, if the data is if the data is there, or if some gases are there, some liquid is there, so that all things which we want to sense or which we want to get the information, that we called as analyte. So based on analyte and mechanism, so sensors are divided into two parts, physical and chemical sensor. In physical sensor, we can say that optical sensors are there, pressure sensors are there, magnetic sensors are there, acoustic sensors are there. And in second type, which is most important type and on which I am working, that is gas sensors, humidity sensors, biosensors, and ionic sensors. Yes, you can, you may predict biosensor also chemical sensor, because all the chemical reactions are occurring there. So if we bifurcate these 5 points I have told you in the first slide, you can see that for the measurement, we are having different kinds of sensors. Okay, for the measurement of chemical components, we are having different kinds of sensors. For the measurement of biological things, we are having. For the measurement of acoustics, electrical, optical, mechanical, magnetic, thermal, various measurements are having in a sensor group. So in the form of energy or power, we are having different sensors. Those are the thermocouples, piezoelectric, photodiodes, thermosistors, and all those things. There are some signal conversion sensors are also there. These are new kind of sensors people are working with, and other outputs related data are here. The most important thing in the sensor is their specification. Based on specification, we will get the idea. So majorly there are 7 specifications, but however, Kirti madam has told tremendously about the specification and the parameters of sensor, so I will not go detail in those. So these are some specification and parameter. Now I will come to you. If we are talking about sensors and all these things, what we are having. Okay, so majorly sensors are used to control the pollutions and to get the quality of material and to get the quality and monitor that quality. But what we are going, okay, so what we are doing, our government, specifically Maharashtra government, is having Maharashtra Pollution Control Board. Okay, so they are having this much big sensor. So 500 centimeters square, 500 square meter, this area is there, and you need this much big sensor to get the idea of the environment, and you will get the environment of only that area or local area. But what about this? What about whole city? So in every city, Maharashtra government and all the governments have put only one machine, and these are so big machines. So these are not good, and we cannot get the exact data what is happening few kilometers far from these sensors, and we will not get the exact data. And if you see the data they are giving, even though we are not getting exact numbers also. So you can see here the values are 000. So it should be very pure system if the values are 0. But however, the values are not 0 and our sensors do not work properly. So I live in South Korea, where in every on every street we are having like these sensors. Okay, so these sensors are based on color. So yellow, green, blue, and red sensors are there. They are divided into PM 2.5 and PM 10. So PM 2.5 and PM 10 are the particulate matters. These particulate matters are the pollutants in the atmosphere or different types of species in the atmosphere. Those can be come into the atmosphere, and those can toxic for our health. Now again, I can see that on every street, okay, if the sensors are there, they are also not sufficient. So what we need? So what we need is, we need a very specific sensor, those we are having with our mobile or with our shirts or with our clothes, we should have some small chip with us. So if we can wear on it, or if we have it, that sensor that gives us the exact information about the atmosphere and my health. Okay, so these are some problems. Now I will go to directly some other point. Okay, because if we relate to the problem, then we will not go. So what I will do is I will tell you about the information about what are the sensor industries are doing. So Figaro is the biggest company of sensor that gives you any kind of sensor. Okay, so Figaro is the biggest company. Second is Alphasense, and you know about the General Electric. General Electric is the big automobile industry. Those are also in sensor industry. So before 80s and 90s, there were very big sensors, and there were no market of sensors. But after 90s and 20s, now in 2020, the pollution is the big issue, and all we have is sensor. Okay, so to get the values, or to get away from toxic things, and to get controlling and monitoring our health. Okay, now in 2021, the World Economic Forum has given data about these companies are working on sensors. So now we can say that our technology people are working for atmosphere and our health monitoring. So we were having problems, the government are issuing these solution, but now some commercial companies are giving solution very greater than those. Okay, so I will tell you about few companies. So first company is Google. This is the Google car that is without driver. It is moving and going everywhere in a whole world. Okay, this car is having about 300 sensors. Okay, and these sensors can measure atmosphere. These sensors capture the photograph. This sensor tells you about the area. This sensor gives about the radar system and all the things we need to do. Okay, now similarly to that, Mitsubishi in Japan are having their second company, that is Theon Sensors. These Theon Sensors are working on Defense Institute. Okay, are working on defense. So they are having many defense institute, and on those defense institute they are working on different kinds of sensors. So they are optical sensors, they are gas sensors, they are proximity sensors. Okay, there are imaging sensors, and this we all know. Now they are in market. So Apple and most of companies are having watches with some sensors. Those can tell you about your health, your heartbeat, and all those things. Okay, so these sensors are the newest sensors. So the big companies are now behind some sensors. So we are having 3 generations of sensor. Generation 1 was very simple generations of sensors. In generation 2, we are using nanotechnology, and we are making thin films of sensors. In generation 3, we are having the flexible devices, wearable devices, and we are having MEMS, the micro electromechanical sensors. Okay, so these are some sensors which we are using in industry, but now in new age we are going to study different kinds of sensors. So some of sensor we have made in our lab that I will show you, and I will discuss you quickly. Okay, so some of the sensors are gas sensors, some of proximity sensors are there, some touch sensors are there, some flexibility sensors are there. Okay, so before that, what we have noticed in our lab is the problem with the sensors are this. So selectivity of any species. Okay, so if we are measuring typical gases. So that typical gas should be sensed by your sensor, not another gas. So selectivity is there, power consumption is there, the sensor life is there. Sensors are having very low quality. Okay, sensors are very low quality about the lifetime, because all the gadgets we are having, those will go to the minimum 3 to 4 years. Okay, the mobile will go to the 3 to 4 years, but for sensor they are having we are having very bad quality. In 2-3 months or 6 months the sensor will die. So effect of humidity is there, atmospheric change is there, limit of detection is there, flexibility and variability. So these are the problem, and what we are doing by issuing this problem, we are practicing some different kinds of sensors. Okay, so I will show you those sensors. So I will skip this part. Okay, so first of all, I have made some gas sensors, okay, on silicon based substrate. Okay, so indium oxide based gas sensors we have made. You can see here the porous and hollow indium oxide nanocubes. Okay, so these indium oxide nanocubes were deposited on this substrate, and you can see that the substrate is there and micro wiring is there. And you will, when the NO2 gas, nitrogen dioxide gas, which is the most toxic, and what we says, most toxic gas which are coming out, emitting out from the industries are measured, and we got some great results. And you can see here that for different gases, acetone, CO2 and NS3, they are having very low sensitivity, they are having very low response. But if you see about NO2, NO2 is about 3500. So our sensor is very much selective to the nitrogen dioxide. So if we can use these sensors in industrial area or near to some equipments or some labs, so we can get that the nitrogen oxide is coming out of that and how much is the concentration. So likewise, we made different kinds of sensors. This is the conventional Taguchi sensor we made, and from this Taguchi sensor we made the sensor eNose. Okay, the sensor eNose is a system where we are having different kinds of sensor for the different kinds of gases. Okay, so we are having minimum 6 sensors at a time. We build those sensors. Okay, after this, while making this conventional and very typical sensor, we are also working on flexible sensors. So the flexible sensors are the device which are applicable to the any body, and also they can be freestand seamlessly on with very high mechanical properties, just like bending, twisting, stretching, folding. Okay, you can see here. Okay, these are the substrates. Okay, this substrate is PI, polyamide, which is kind of plastic or you can say polymer. Okay, so sometimes we use polyamide, sometimes we use PET substrates. Okay, sometimes we are having some flexible silica. Okay, you can see here we have made one sensor. Okay, that sensor is stretchable, bendable, foldable and twisting. So by anyhow your body moves, if I wear that sensor on my body, anyhow my body moves, that will not affect the sensor. So you can see here also, this is the preparation of the sensor. Okay, on PI electrode we are having gold electrode and we are having some zinc oxide material, and you can see that if I bend the sensor of about 10,000 times, even though that there will be only 4 to 5% of change in a sensing results. Okay, and only what is the difference between the flexible and simple sensor is that after using flexible sensor, these sensors will change the response and recovery time, so that the sensor will responds very slowly, okay, than old one sensor. However, we are having the benefits of flexibility so that we can wear those sensors, we can have sensors on any kind of body, we can attach those sensors anywhere. Okay, with this, we are also working on eNOS sensor. I will tell you eSkin sensor is there. So eNOS or eSkin sensor is a kind of new generation sensor. So these sensors can be attached on your body. Okay, by using some technology, you can attach on your body. Basically, we are attaching the sensors on body by using some plastics and some polymers. Okay, so you can see this is the flexible substrate. Okay, we are having OPET. These are the flexible substrate. So what we do here is we are having two substrate. We take two substrate. In between those two substrate, on one substrate we mask some contacts, and on those contacts we are having some sensing material, and we sandwich it, and to stick the skin, what we do is we use the PDMS. PDMS is polymer. This image I have taken from internet. Okay, so we cannot share our image because it's an industrial project. So some of results we have published that I am showing you. So this is the sensor. Okay, so this sensor was made on PI substrate, that is the polyamide substrate. So we have made those sensors, and this sensor can be attached to skin, and that will give you about the information about the humidity, and also we are having the sensor for ammonia. Okay, so we made e-skin sensor. Okay, the sensor which can be which is stickable, which can be emulate on your body, and which will give you idea about the atmosphere. Here one new idea is there. So we are having these pads. If we are attaching our sensor with these pads, so we will get the idea. Due to the humidity, we will get the idea about what the leakage is there, or we have to change the pad. So different kinds of these ideas are working. We are working on it, and we are having these kinds of sensor, and we can fabricate for any kind of gases and any kind of chemicals. So just like this, now we are having for we are working for some blood. Okay, so if there is some blood coming outside your body or something is there, then you can precisely know this. So again, our lab is again working on micro electromechanical system, that is the MEMS. MEMS just are the same machines, but they are very small, okay, in size. So MEMS is simple electrical or simple electronic equipment with very small size, okay, and they are having very high efficiency. So we have fabricated like this. You can see this is the MEMS sensor. Okay, so these MEMS sensors are having very low consumption of power, and this very low consumption of power will gives you extra power or extra life for your sensors, and will consume power very less. So sometimes we use these kinds of sensors, and we can also buying these sensors directly from some industries, and just on these sensors you have to build your system by using some physical technique. I think many of people have heard about MEMS technique. In that MEMS technique, we are having some photoresist, some deposition will be there, some lithography will be there, some etching will be there. So we take these commercial heaters and all these things, and we build the sensors like this. So this is the one kind of sensor we are having. Okay, so again, this is my old work. Last year we have published it. This requires no any power consumption. This is just a button type sensor. Okay, if we are having some different kinds of toxic gases and some different kinds of liquids, specifically ammonia liquid, then the color change of that material will occur. So that color change, the optical color change and the electrical change, okay, will give us the idea about the gases, okay, the presence of gases. So here we are having some electrical properties, okay, which have been changed, and here you can see when I have exposed to the ammonia liquid or ammonia gases, the color is also changing. So if we are having some button, okay, and we will put that button on our clothes, and we are working in some ammonia industry or in some different industry, if the ammonia is leaking, leakage is there, and then we can get the ammonia. Okay, so again, okay, so some of wearable sensors we are doing. I will not go in details. I was trying to go in details, but we are having we have fabricated transparent sensor. This is the wearable sensor. This sensor is having some stickers. Okay, so this is the graphene based transparent sensor you can attach on your body. Okay, but these require some electronics. These are only sensors, so you can attach on your body, on your shirt, on your pant, or on your lab coat, or on your working any clothes, or simply on your body. Okay, so these are some wearable sensors we are having, and we are making these sensors. Now we are working on some nylon based sensors. Okay, so nylons we all know. So we are having some mesh, some typical mesh we are taking, and we are depositing some nylons on that, and those nylons are finally converted to the different substrate to the sensor, and on those substrate we are depositing graphene or another carbon based material to sense the gases, to sense some body changes, or to sense the temperature. Many things are there. So our group is also working on pressure sensor. Here I have shown you different kinds of pressure sensor people are working, but in our lab we are working on very small pressure sensor. You can see here. Okay, these pressure sensors are having different kinds of material at the different level, and if we get the pressure sensor, you can get the idea about any pressure. Okay, any pressure, and you can attach with your computers or electronic device. You can also get the recognition of the emotions. You can also get the frequency of your voice, and also the pressure of breathe air coming outside gives you the idea about, okay, how much pressure is there and how much air is coming out of your body. Okay, so with this I think this will be so this is the second last, and our group is having some small proximity sensors. You know the proximity sensors. The proximity sensors can detect any object which is near to that sensors. So these proximity sensors are capacitive, inductive, and electromagnetic. So we are mostly using electromagnetic and capacitive sensors, and the nano devices of proximity sensors are also fabricated in the lab. Okay, so this I have taken from internet. So like this we are developing in our lab. So this is the commercialized electromagnetic proximity sensor that will give you idea about the near object when it comes. Okay, so another there is some memorandum of understanding between some industries with us. So Bosch is very famous industry, and those have developed in collaboration with Samsung, and in that collaboration with Samsung, our team was there. So if we see here, we are having the sensor. This sensor is not simple sensor. This sensor is joined with the machine learning and artificial intelligence. So if I got these sensors, I am having the electronics related with my PC, which is connected to the internet. So if I get check any sensing, okay, the coffee beans are there. If I check the coffee beans in different type of coffees, if we use, so that will give me different kinds of information. And after getting in different kinds of information, the company will get my data and will use and will change all the parameters and all the things. And if someone wants to sense the coffee, then he will get the related data, and he can also recognize it. So he will get the reference. So by using machine learning and artificial intelligence, if someone is checking some typical kinds of sensors, that data will go directly to the company, and that data will be used to the another users anywhere in the world. So this is the small sensors, the MEMS based small sensors are attached to this actuator system and electronics, and that can be operated on mobile also and PC also. And the whole thing of machine learning and artificial intelligence has been done by using what has been done by using pattern recognition. Okay, so in pattern recognition, what we are having is we are having tremendous amount of data from whole world, or we are having tremendous amount of data of different gases, different species. But by using the machine learning, by the mathematical simulation, by the Python simulation, we can collect the data and we can organize the data. And that organized data will give you the actual representation of presence of gases, presence of liquids, presence of anything that you are sensing. Okay, so this is the pattern recognition. Pattern recognition is new kind of technology that is coming with the machine learning and artificial intelligence. When you are having all the things, so when you are having different kinds of sensor, all sensors are sensitive to all gases or all spaces, but you have to choose the best one. So in class, if we are having, okay, in class, if we are having 5 to 6 type of students, and all those students are intelligent, but we have to check the most intelligent one, then we need the process like this. Now this pattern recognition and artificial intelligence we are using is kind of connecting the server to the whole world. And when the whole world is connected by the machine learning and artificial intelligence, the all data will collected and all data will serve to the all people in whole world. Okay, so that's very important thing we have started, but still there is big work to do on this. Okay, thank you. I'm extremely sorry about the problem arises due to me, and also I'm very thankful to Dr. Latte sir and Dr. Arif Sheikh sir, and also the chairperson of this session. Thank you.
Okay, okay. So now there is some question from Pratiksha. Pratiksha, you want to ask question, right?
Yes, yes, yes.
Please unmute and you can ask question, Pratiksha. Or you can write your question in the chat box.
Sir, I wanted to ask, sir,
Yeah.
first of all, today the information that Krishna Pawar sir gave us was very much informative. But sir, as you told us while explaining that sensors have a very weak lifespan, or it's a small lifespan, and the
Yeah.
development project that is being conducted by you is of e-skin sensors. Sir, then as we know that any development which takes place in whether it is in science or in nanoscience, it's for the betterment of the people. And
Yes.
being a part of a country like India, if we know that sensors preparation which are being used for in a biological method will require the elements which are highly costly, and if their lifespan is too less, then how can we use it? So it is better if we can apply these sensors in our cell phones or what, because nowadays everyone has a smartphone, and if we can apply this in that own cell phone, a technology or a sensor which can detect and give us notification, then won't it be better?
Yes, definitely, Pratiksha. But for this, your mobile can be sensor in future, but now it is not possible. But your mobile can be actuator, but for nowadays your mobile cannot be a sensor because sensors are somehow big and your mobile is not having that much of space. And definitely if you see, if we need some charger, we are having some mic area. Likewise, for sensor we need some holes on your mobile, and that holes or that extra area which is connected to the should be connected to the environment. And every time after some days or after some months you have to change it. So
Okay,
for
sir.
that reason many companies are not okay, are not allowing for adding sensors in mobiles.
So then can we develop any kind of watches or some means those who are interested can use them?
Yes,
And
yes,
is
we
there
are having. So I will tell you, right now we are working on industrial project. In between, I have shown you different companies. I will tell you, you just hold for 10 years. You will get a tremendous different kinds of sensors. You cannot expect that, because
okay, sir.
different kind of industries we are having have patented different sensors right now, and they need some time to commercialize and to get very cost effective. Even though in our lab we are having different kinds of sensors that are very good, so we have given those information, and my professor has patented it with the Samsung and Hyundai. But the problem is that these sensors will be very heavily priced, and
Yes, sir, that's the main
for
issue.
the
Means I wanted to
yeah.
ask that question only. Like, sir, a person who is means having a good income can buy such kind of sensors very easily, because for him, his life is more important, and he can think that okay, if anything happens to me, I have to pay to hospital. Then better for precaution, I can buy a sensor and take care of me. But in India, it's a developing country, and many people are not that rich, so they can afford this kind of thing. So, can we create any other nanomaterial or develop such science that for basically we can make it available for people with minimal income also?
See, Pratiksha, I'm the
Simple
man of
question.
material science, and as per my knowledge, we are having right now very sufficient materials, and we people have developed very sufficient materials just like graphene, CNTs, and some metal oxides, some metal sulfide, perovskites, and all these things. And it is very much difficult to have or to create some new materials. Okay, and that should be very highly sensitive than those materials. So if material we invent, from invention
to use in industry, we actually need minimum 30 to 40 years. You know, the graphene is very magical. The fullerene is very magical. CNT is very magical. But right now, from 2004, it has invented. From that time to this time, we are unable to get in our industries. So very much difficult to have it in our hand. Some normal people are having these things in our hand, but it's okay that we can develop, and we are at lab level, or some of the industries have gave different kinds of sensors, and you can buy that. Okay, so I told you about the Figaro. You can go on Figaro system, you can give your specification, and they will automatically select the sensor, and just you have to purchase it. And after purchasing it, wherever you are, that sensor will come to you, and you can use that sensor.
And sir, one more thing I wanted to ask you, that while explaining, you said that you are the institute in which you are working, you are trying to develop a nylon on material with combination of sensors. Sir, using such material means every electronic item or any particle has an effect on our body. So will these sensors also affect in adverse way to our body?
The old sensors were there, but now some new sensors are there. These are eco-friendly or environmental friendly, we can say, and most of sensors are carbon based, or some eco-friendly materials are there, or there are some materials which are not too much toxic to us. And that's why what we are working on, and what whole sensor industry is working on, is having some material which is not toxic, and that material should have very great sensor response, and also that material can detect and gives us the information about the toxic things. So it is very hard. The person should be non-toxic, that person should be great, that person should have high performance, and also that person should detect the toxic people around them.
Okay, sir. Thank you, sir, for the information.
So in future we can. Thank you.
Okay. Okay. So is there any other question? Okay. So if there is no question, let me thank to the speaker, Dr. Krishna Pawar sir from Hanika University, who has nicely presented on the new age nanosensors. So thank you, Krishna sir.
Yes, thank you. Thank you. All the people from Amity University, and special thanks to the Vice Chancellor of the university, convener Dr. Latte sir, and co-convener Dr. Arif Sheikh sir, and the session chief, and most importantly my student friends. Thank you.
Okay, thank you so much.
Okay, sorry for the late and trouble.
Okay, thank you. So,
Thank you.
So, dear participants, now the first session is over, and there is a lunch break now from 1 to 2 p.m. And then after lunch break, there are 3 more presentations are there. So I request all of you to rejoin at 2 p.m. So by the time, have a lunch. Thank you.
Okay, before we go for lunch, let me thank Professor Praveen Warke, Professor Suhad Jezurikar, and Dr. Arif Sheikh for chairing the session. Thank you. Thank you all. Thank you, Suhas. Thank you. We'll have a break of lunch. We'll be starting our next session exactly at 2 p.m. So requested all participants to be here, or you can rejoin at 2 p.m. Thank you. I'm very pleasure to introduce new session chair of this particular session. We have with us Professor Dr. Bhaskar Sate from Aurangabad University, Dr. Babasaheb Ambedkar Marathwada University, formerly Aurangabad University. He is a faculty in chemistry department, He has done a lot of work in chemistry, material electrocatalysis, and a PhD from National Chemical Laboratory with Professor Dr. K. Vijayamohan. He is very well-known electrocatalyst in chemistry in India. And we have with us another session chair, Dr. Niranjan Ramgir, who is shortly joining with us. He is currently working in Bhabha Atomic Research Center, Mumbai. Now I request Professor Bhaskar Sate to chair the session. Dr. Bhaskar Sate.
Good afternoon.
Good afternoon, sir.
Yeah, good afternoon. Thanks to organizer Professor Datta for giving me an opportunity to be chair this afternoon session of International Workshop on recent trends in functional nanomaterials for technological applications, organized by Center of Nanoscience and Nanotechnology, Amity University, Mumbai. So for this session, we have the three speakers, and first speaker for this session, the speaker number 6, Professor Aniruddha Basu. He did his PhD in science in 2017 from National Chemical Laboratory, Academy of Scientific and Industrial Research, India. His master is from University of Delhi in 2010 in specialization of organic chemistry, and bachelor from the Calcutta University in 2008. After PhD in 2017, he joined as a postdoctoral fellow as an NPDM of DST, that is in Indian Institute of Science, Education and Research, IISER Pune. And after that, he moved for the postdoctoral studies in January 2018, and till now he is working at KAUST Kusat Solar Center, KSC, King Abdullah University of Science and Technology, Saudi Arabia. It's contributed more than 20 publications that has published in reputed journals like Nature, having the 4, American Chemical Society ACS 3, RASC 5, elsewhere 3, and Wiley 8, currently holding more than 800 citations with H index of 13, is as per the Google Scholar data, and submitted a provisional Indian patent file on dope carbon nano onion film on as a saccharoid for stabilizing lithium metal ion as an Indian patent. So this, I request Professor Aniruddha Basu for take a charge of this session.
Dr. Aniruddha, you can unmute yourself and share the screen.
Yeah. Can you hear me?
Yes, yes, yes.
Okay. So thank you for your kind introduction. So I will be talking about today about one of my recent works here.
Can you share your screen? Screen is not.
I'm trying to, yeah, I'm sharing. Yeah.
Okay.
Just a second. Yeah. Yes. Yeah. Can you share my see my sharing?
Yes. Yes.
Yeah. Okay. So I will
just
be talking about.
Make it slideshow.
Yeah.
And it will be visible for.
Yeah. Is it fine? Yeah. So yeah. So I will be talking about one of my works on the p-type doping on the blend small molecule polymer blend transistors. So where we actually did the blade coding on those. But before going into the detail of the work, I just wanted to introduce about the transistors, how they work, and why they're important in our life, basically. So I said life because so we are actually surrounded by the different type of electronic gadgets, from like so-called electronic gadgets like computers, mobiles, and tablets and all those things. And also we have some medical equipments which are also kind of electronic devices. So these electronic devices are basically run by the motherboard. So which is it's a very lame language, we can say that the motherboard or the circuitry, electronic circuitry, which actually runs the all the electronic devices. So this motherboards have different components ranging from transistors, diodes, LEDs, capacitors, and all those things. So all of them have their own working principles, and they are actually doing make the whole system works. So out of them, so one of the most important or interesting component is the transistors. So we will be talking about this the particular transistor today. So this is a 3-terminal device, and it has the transistors are kind of different kinds are available, like MOSFETs, JFETs, and all those things. So here we will be talking about mostly MOSFET type transistors. So recently we can see that this electronic gadgets are becoming flexibles, because the flexible, the overall, it's making the new generation electronic gadgets like flexible TV. We can see recently Samsung and LG has launched a flexible TV and all those things. So we need to make the components flexible as well. And also biomedical applications, there we need some wearable devices that also needs to be flexible. So the components, and also like components like transistors, needs to be flexible as well. So making the transistor flexible, we need the component, like the building components of the transistor has to be a soft material. Like if we cannot make flexible transistors using silicon or maybe metal oxides, so we need to go through, metal oxide we can use in some cases, like if we make it nanoparticles, so nanocrystals if we are using. But one of the most easiest option is to switch to the organic like polymers or small molecules. If we use this kind of polymers or small molecules, the devices can be easily be flexible devices. So here we will be talking about the OFETs, the organic field effect transistors. So just I will briefly tell you how the organic field effect transistors works. So it's basically it has a 3 electrode system, as I told you. One would be gate and source and drain. The source and drain is attached to the semiconductor, and the semiconductor have attached this is the semiconductor, and it is attached to a insulator film, which we say dielectric, and the gate electrode it attached to the dielectric. So how it works? Let's have an example for p-type semiconductor, p-type transistor, where we have the semiconductor as p-type, and the semiconductor is p-type, and we apply a negative gate voltage on the 3rd electrode. So in this electrode, we are applying negative voltage. So this insulator will polarize itself to form a positive charge over here and the negative charge at the interface of the semiconductor. So at the interface, when we have the negative charge, the holes from the semiconductor will accumulate. So will be available for electron transfer. So ultimately, what we have, if we apply a swiping voltage from source to drain, we will find a constant electron flow. So overall, the current we will get the current. So as we keep on increasing the gate voltage, more and more electron holes will generate over here, and the current will increase. But obviously, a certain point it will saturate, since once the holes are no more be available to accumulate, so it will stop. It will saturate the current. So, and the reverse thing will happen for the n-type. So there are for several decades this organic field effect transistor research has been going on, and you see as you keep on going to the recent year, the mobilities of these particular devices, OFETs, are increasing, and it is almost reaching almost 100 mobility. But these data are not all the data are reliable. And a recent study from Patterson et al., they found that most of the devices claiming very high mobility values are not reliable yet. So the reliable p-type or n-type transistors mobilities values are lying around 20, not more than 20. Even it is rather below 20, 15, 10 to 15 would be more reliable values. So, and also if we can see, like if we use this kind of organic field effect transistor for industrial application, like regular gadget application, lab scale 10 to 15 mobility would be enough to make a very small powered device circuitry. So anyways, so for organic transistors, we the semiconductor layer can be formed using either polymer or the small molecule. They have their own advantages and disadvantages. Like for the polymers, they are very highly soluble in most common organic solvents, and so it will have a very easily solution processable. And also, since they form amorphous like films, so the film are generally very homogeneous, and the device parameters will found uniform throughout the devices. But this kind of polymers generally suffer very low mobility values. So generally the reported value is probably highest value would be around 2 or 2.5 for polymers. But on the other hand, the small molecules, they are very high mobility devices. They can form very high mobility devices where the mobility of the devices can be higher than that of the silicon. But this kind of small molecules, generally small molecules are highly crystalline. So if we go for solution processing, it is very difficult to make a film out of it. And also, if we could able to manage to make a film, it will not be that uniform. So people try to blend them to take the advantages of both of them, both this polymer and small molecule out. So there are two ways: either use add insulating polymer and small molecule blend, and the conducting polymer and small molecule blend. So in this work, we use the second approach, because if we are using insulating polymer, you are actually suffering from a low current problems. But anyways, so we use the conducting polymer small molecule blend. Here we use C16 IDTBT polymer and C8BDBT small molecule. So we need to blend them so that they have the comparable energy levels. Otherwise, it might conflict the overall process. So here in this case, we use a dopant as well. So this dopant is basically it's a charge transfer dopant. It actually take the electrons. It has a very low lying LUMO. Here you can find it is the LUMO value of this C60F40A is lying around the C8BTBT and C16 IDTBT HOMO. So it effectively pull out the electrons from the HOMO of this small molecule and polymers and create the holes. So ultimately, so the overall the charge, the amount of charge is more. So the overall current should be increased with the doping of this particular dopant. So here in this case, we made the devices using blade coating. So why blade coating? I'm just giving you a different coating techniques, which is generally available for solution processing. It's the deep coating, spin coating, slot die coating, blade coating I told you, and bar coating. So it's in this case, you can see it's mostly we use the spin coating and blade coating, and they have their advantages and disadvantages. The disadvantages I marked it as a red, and the advantages I marked as green. So it will be easier to understand. And where this is, it lies in between, I marked it as yellow. So here you can see for the blade coating, it is a very low cost system, and the processing cost is pretty low. It is highly scalable, and the complexity is medium. They say, but the thing is that since the technology is evolving, so the complexity will be will not be an issue in maybe another 5-10 years. And the uniformity, yes, it has uniform, but not good as other techniques, but that also can be overcome in the coming years. And the patterning, it has the limitation in the patterning where we can pattern only the thickness in that means we can make a different thickness in one particular film. We can have a step of the thicknesses. So with this particular blade coating technique, and it can be it can use in the flexible substrates for the roll-to-roll coating. And the solution wastage, it is showing moderate, but I would say it is low because like we need only 5 microliters to coat 1 inch by 1 inch substrate. So it is relatively quite low. And the drying time, it is also, they said, slow can be increased by heating. So that is the most important parameter for the blade coating, because if you here you can control the drying time. So basically what happened, like if the film is instantly drying, your microstructure, you won't have in control over your microstructure for the polymer or small molecule films. So here it can be slowly, you can control the drying process, so you can control the microstructures as well, and the coating speed is pretty fast. So here we compare the spin coating and blade coating in our case. So how the blade coating works, it is a meniscus guided coating. So we put a blade on the just on the substrate on a particular angle, and we put the solution between the gap between the blade and the substrate, and we move the blade. So it forms a meniscus which actually coated over the thing. So this is the structure we have used, device structure we have used for this particular work. So we have source, it's called bottom electrode top gate device. So here we have the substrate, and we form a source drain electrode with the gold with shadow mask using thermal evaporation, and then we blade coat the organic semiconductor and the dielectric film, and we put the gate electrode aluminum as a with thermal evaporation as well. So the outline of my talk would be like making the film quality and the device comparison with the spin coating and blade coating devices. Then we extend this work to the doping of the of this particular system, and we only showed the blade coating, how the blade coating is used, and we compare the charge transport and the organic bent films microstructure with the doped and undoped films and the summary. So here is the microstructure of the blade coated films, spin coated films. I'm sorry, spin coated films, and you can see the islands are forming here, and here is a blade coated film. So here you can see, so basically just to introduce with the system, so we are using the small molecule polymer film. So this particular film has a tendency to form a phase separated film. So it happens as we as you keep on like you make the film and while drying, the polymer goes below of the film, and the small molecules go as the top. So there and it forms a crystalline domains at the top of the film. So it looks like this. So this particular thing has happened. The C16-IDTBT goes at the top, and this is the elemental mapping of the EEL spectroscopy, electron energy loss spectroscopy. So there we can see the C8BDBT film is forming at the top, and the C16-IDTBT at the bottom. So here these islands are formed using C8BDBT, and for the blade coating we can see the islands are bigger. So that means we have a lesser grain boundaries and the proper charge transport. And in the height profile with the AFM images, we can find that the heights, the microstructure heights are more uniform compared to the spin coated films, and it is lying around 5 nanometer mark. And the height is around 2.83, which actually squeezed in case of blade coated films, and showing it is a more compact film. And you can see the device quality, and we found that the device is much better compared to the spin coated film. The spin coated film, we found the mobility is around 2-3 centimeter square per volt per second, but for the blade coated film, it is the highest mobility we could achieve around more than 6 centimeter square per volt per second. So the overall device performance using the blade coating, the blade coating is not only giving us the flexibility of the process, but also it is giving us the better microstructure, which actually translated in the device performance. So later we use the blade coating for the doping study. So here we use 4 different doping percentage and compare with the pristine one, and we found with the doping the overall microstructure is getting bigger, and also it is minimizing the gaps between the 2 microstructure, and also it is overlapping on one another. And see the as you keep on increasing the doping percentage, the overall overlapping of this particular microdomains are getting more and more. And here is the height profile. We found that till 0.75, the microstructures are getting better, improving. But as we keep on increasing the doping percentages, it is again kind of scattered. So probably the 2 and 4.25 will not work as good as till this 0.75, and we will find this eventually. And you can see the RMS roughness as well keeps on increasing, and the terrace height is also increasing as we keep on increasing the doping percentage. So here is the Kelvin microscopy, where we found the work function and we found that as we keep on increasing the doping percentage, the work function is getting actually getting higher since it is a negative EV, so it is getting lower. So the work function is getting deeper in the zone. So here we actually found with this particular data, so the 0.0% and 0.75%, they are like 0.75% is basically the best device we found. And here we comparing these two more closely, and we found that they don't have any not much change in the RMS roughness values, but the microstructures, the height distribution is getting better and more uniform in case of 0.75% doping. But once we use the GVAC study, so in the GVAC studies, basically it is showing the crystallinity of the microstructure. We found the crystallinity is not changed. The crystalline domains are maybe bigger and smaller, but microstructures may be different, but the crystallinity overall, CA-BD-BD crystals are not changing. So this is an interesting finding in this case. And so then we see the device performance, and we found the device performance is improved. So from 6 centimeter square per volt per second mobility for pristine device, we found highest almost 14 mobility, and which is ranging around 10. So which is and the average mobility is ranging around 10 for the p-dope, and this is a very interesting finding. So this particular change is not like we cannot say only the microstructure can be like the only reason for this particular increase in the device performance. So we trying to study the low charge transport mechanism. So here we use the low temperature. So we decrease the temperature till 100 K. We take and check the mobility values for each devices. So we use it for the pristine and the p-doped. So we systematically decrease the temperature, and then we comes back from 100 to 300 K. So we start from 300 K to 100, and then comes back to 100 to 300 K. And we studied the mobility values, and we plot them, and we found this particular graphs. So let me explain the graph. So basically what happens as we keep on increasing decreasing the temperature, we found generally for organic devices, we generally see the mobility decreases. So this is because they call thermally activated transport. So this is because, so as we keep on decreasing the temperature, the other parameters like the contact resistance and the charge transport these actually have a detrimental effect on the device. These actually increases, and it forms the detrimental effect on the device. So it decreases the mobility values of this organic devices. But C8BDBD devices, if there are studies on the single crystal C8BDBD device, they are generally found to increase the mobility values as they keep on decreasing the temperature. This is called band-like transport. So this band-like transport we could find in our pristine device as well. So as we keep on decreasing the temperature from 300 to 210 K, we found the mobility values increases, and then it decreases pretty sharply. So what does that? So and for p-doped devices, we found that increase is 140 K, and really what happens as we use the dopant, is it basically improves the microstructures of the devices, which actually minimize the defect states. So defect states are generally responsible for anomalous detrimental effect on the devices. So as we decreases the defect states, so we shift this critical temperature where the band-like transport to thermally activated transport switching, this critical temperature TC has been shifted to a lower temperature. So that means the overall charge transport is getting better in case of doped devices, which actually in turn improves the mobility of the device. So in summary, we can say that the coating conditions affects the crystalline domains of the blend films, and the quality of the blend films were way better in case of blade coated devices compared to the spin coated devices, and that actually translates in the device performance as well. And after molecular doping, we found that the blade coated system, we use the blade coated only in this case, so we got a better morphology, and the charge transport in turn is also better, and it actually deactivates the trap state in case of in the molecular level. And the charge transport is basically improved due to charge carrier generation and trap state, deactivation of trap state, as I told earlier. So this doping is a versatile tool, and people are using quite regularly this kind of doping approaches. So this is my group where I'm working. It's my professor. I'm working under him, Professor Thomas Anthopoulos, and this is our the whole group. Thank you for your attention, and open to any questions.
Thanks, Anuruddha. You have completed in time, actually. So now the session is open for discussion. Just one or two quick questions. Participants, let me check chat box if anything is there or not. There is a question from Shubham. How do we get to know the homolumal level of unknown blended samples?
Unknown blended samples. Yeah, I have seen the one of its structure. Their gate is fabricated. And okay, the first question is, so generally we there are several ways you can find the so we don't use unknown blended sample. So we generally use we know but what are the components we are blending. So you can take, if you want to take if you want to know the homolumal levels of a particular substance, so you can see you can use the SCLC and other techniques to check the homolumal levels. So, or maybe I forgot one of the techniques people generally use for that's I forgot. I will tell you. I will tell you I forgot. Anyways, so there are other techniques where you can use the homolumal levels, but in case of if you want to use directly the blend, you won't get the particular. You will get only one hybrid homolumal levels. So it will not be separated for A and B. So you will get a hybrid homolumal levels with this. And I have seen one OFET structure, their gate is fabricated at the base of the transistor. There is, yeah, exactly. So they basically, there are 4 different OFETs can be fabricated. Bottom contact top gate, top contact top gate, bottom contact, and bottom gate top contact. So in my case, if I could share quickly, I will show you. So basically, if you go to the, sorry, you go, yeah. Why it's not working? Yeah. So if you go here, you can see this is bottom contact top gate. Then you put this source and drain on top of this blue film, you will have top contact top gate. Then you put this gate on back and the dielectric on top, then dielectric here, gate on underneath of that, you will have bottom gate, top bottom contact, and you put this on top of this blue film, this source and drain, and gate on the bottom, you will have bottom contact top gate. So these are the nomenclature you can say we use. Yeah. So, and it actually affects the, it depends on the system you are use. We choose the different this thing for different structures. Like in this case, as we said, we have a phase separation. So our semiconductor will go, the main semiconductor will go on the top. So we need the semiconductor dielectric interface at the top. So that's why we use the top gate. But other cases you can use bottom gate. So there are things are there. So yeah, any other question?
Neeraj, hi.
Hi, Arif sir.
I have one question. What is the stability of these transistors?
Yeah, so the thing is that we actually, in this case, we actually provided the self-life stability. So I made the devices late 2018, and recently I gave one of my colleague to use this particular device, and it is working. But that was throughout inside the glow box. And since this is a P-type devices, I think it is quite stable. So P-types are generally quite stable. So maybe outside we can use without any encapsulation. We can use for a month or so, and with encapsulation, it will definitely increase the device performance. Yeah,
Okay,
one more
you.
question I found. Any question? Any more, Dr. Arif?
Yeah, one more question is there from Pratiksha Chaur.
Yeah.
She is asking if the dopant is not following any of the character used for studying the property, who can we adjust it for any other dopant than C6F48?
So, so what I understood that you wanted to use a different type of dopant. So actually, the dopant system is depends on dopant is depending on the, we use the dopant depending on the system itself. So if you are using a different, so let's say in this case we use C60F48 for C8BTBT. So right now I'm working on a different semiconductor small molecule system. where we are using a altogether different dopant. So we need to think before start working. We need to plan. So what kind of system this is and what kind of dopant we are going to use. So in this case, I would recommend you. We recently published a review article, and it's doping approaches in organic semiconductors in chemical reviews. You can read this particular review. So there you will find how the doping and can be used, and what basically dopants do, and what is the physics behind it, what is the chemistry behind it, how it is used for devices and all those things. So you probably will get all the answers from this particular review article. Yeah.
Okay, there are no more questions.
Yeah.
From audience. Dr. Basu has presented very nicely the concept of effect of doping, P-type doping on the microstructures and nanostructures, processing of materials, their charge transfer mechanism, effect of dopants, effect of defect states, and all these things. He compared to different systems like blend coating versus spin coating. And this, on behalf of organizing committee, I say thanks to the Aniruddha for giving your special time for this.
Yeah.
Thank you.
Thank you. Thanks a lot. Thank you.
So the second speaker for this afternoon session is Kiran Botkar. Just before start, I will introduce him. So, Kiran Botkar, he did his BSc in physics from Modern College, Wasi, Navi Mumbai in 1999 to 2000. After that, he did a diploma in management studies from AIMS, Chennai 2007, and diploma in AutoCAD. Working experience is currently working with Icon Labs Private Limited as an assistant manager since 2010 onwards to till date. And is working on the operating environmental scanning electron microscope, EDX, since last 12 years. Have analyzed more than 30,000 samples of different types, also taken training for the transmission electron microscope. He work on analysis of the sample includes the metals, powders, polymers, fibers, paints, thin films, tooths, and bacteria. Tissue cells, hair, wood, paper, oil, gel, and leaves. There are a variety of samples he analyzed. And with this, I request
Yes, sir. Can you hear me?
Yes, sir.
Yeah.
Dr. Botkar.
Yes.
Yeah, it's perfect.
Yeah. Yeah. Good afternoon, everyone. Yeah, I would like to thanks to Dr. Dattatreya Latte for giving me opportunity to present my PPT here on scanning electron microscope. So today I'm going to talk on the basic principle of scanning electron microscope. Before that, I would like to tell about my company. Our company is in an imaging analytical lab where we have a instrument like SEM Quanta 200, and we also have FESEM Quanta 200 coupled with the EDS detector. We have energy dispersive spectroscopy attached to this scanning electron microscope. We also have a facility of TEM Technic-Well in our lab. So we have our team has an experience of over say 20 years in electron microscope. And people from different institutes, colleges, they visit to our lab for testing the samples. People from industries also, they visit to our lab from pharmaceuticals, metallurgies, paint, steel, automobile, and many more. So overview about the scanning electron microscope. First, I will take the introduction, then working and construction of SEM, electron gun, magnification system, then scanning coil, focus unit. So we'll be seeing one by one each of the part of the scanning electron microscope. And at the end, we'll see the application of SEM, that is the scanning electron microscope. So why we need a scanning electron microscope? So as you see in the image, you can see the image of an ant is taken on an optical microscope. So in this, you can see a lack of resolution. The image is not that much clear. The depth of focus is not good. So in optical microscope, there is some limitation to get a clear image or focused image as compared to what we'll be looking at the scanning electron microscopes. So if you see the image under the scanning electron microscope, the same ant is viewed under the scanning electron microscope. So image taken at 150x magnification, the same image when magnified, the particular area that is the eye of an ant view at 1200x magnification. So you can see the depth of focus and the clarity of that image or the object. You can see easily all the features, details on it. So this is what the instrument we have in our lab. It is a scanning electron microscope of Quanta 200. And we can see the chamber view of that microscope where we load the sample. In this chamber, we can load multiple samples at a time. We can load 7 samples at a time if the size is around, say, 1 centimeter of the sample. So we'll see one by one each component of that. So if you see at the top, the electron gun is there. Then we have an anode, magnetic lenses are there, scanning coil. So electron gun here is the tungsten filament that we are using in a scanning electron microscope. The electron beam is shooted from the tip of the filament and it travels towards the anode. The anode is being a positively charged, so that the electron travels toward the anode and they passes through these lenses. So in scanning electron microscope, we have a column where there are the lenses, but these lenses are not the glass, they are electromagnetic lenses. So through which the electron beam passes and then it enter into the chamber and hit the samples. Once it hit the sample, we get different types of signals from the samples and that signals are converted into an image. So we'll see that one by one. So this is how the filament look like, means electron beam, when it's shooted from the tungsten filament, you'll see the grid cap, it is being a negatively charged. The electron are also being a negatively charged. So they repel and they form a space charge over there. And the anode plate, which is being a positively charged, those electrons beam, it travels towards the anode, get accelerated, and it passes through the column and enter into the chamber. So this the characteristics of electron beam. The electron beam typically has an energy ranging from 0.5 k electron volt to 40 k electron volt. So we can change or we can select any of the electron volt depending on the nature of samples, and we can analyze the samples. So it focuses one by one, one or the 2 condenser lenses to get a proper spot size, say 0.4 nanometer to 5 nanometer in diameter. So depending on the spot size also, the image clarity depends. And this electron beam, it scans the sample in raster fashion from left to right in rectangular area of the sample area, surface. You can see a sample on the left hand side and the blank monitor on the other side. When we scan this, after scanning in a raster fashion, the same object can be seen on the screen, which is at lower magnification. The whole sample is visible, so it is at lower magnification. You can see the raster fashion how this sample is scanned on the with the help of this beam. So the magnification is the ratio of the length of the screen to the length of the sample. So while obtaining an image in a scanning electron microscope, so ACM operator need to do the 3 things. So the 3 things are very important while taking an image. So determine the proper spot size. it should be a proper correct focus, and we have to correct the astigmatism. So these three things we have to keep in mind while taking an image in SEM. So if the spot size is not proper, so you can see at larger spot size, the unclear features is seen, though the image is smooth, but the unclear features can be seen over there if the spot size is not proper. So to get the proper or clear image, you have to reduce the spot size. So the spot size means the tip of the beam. We are reducing the diameter of the beam, so which makes the image sharper. Yeah. So astigmatism. Astigmatism is the what we can say when the beam, the shape of that beam is not proper. So we get a defocused image, or it's not in proper focus. Either it's a over focused or the under focused. So to get the proper exact focused image, we have to correct the astigmatism. So electron specimen interaction. So type of signals that we get from the samples, there are secondary electron signals, backscattered signals, and X-ray characteristics. So when the electron beam hits the samples, we get different types of signals from the samples. And those signals are secondary electron signal, backscattered signals, and X-rays. So what are those signals now? We'll see that. So secondary electron signals that we get, those are the signal electrons or the signals. When the electron beams comes and hit the samples, some of the electrons, they come from the surface of the samples and it travels towards the detector, and we get a secondary electron image. And those electrons which are coming from the samples are these secondary electron signals. At the same time, some of the electrons from the beam, they scattered back. When it touches the sample, they return back. So those electrons are called the backscattered electrons, and we get a backscattered image. So here we are getting the two type of image, that is secondary electron image due to the secondary electron, and the backscattered image due to the backscattered electron. So backscattered electron will give us the elemental phase contrast image. So depending on the elements present in the samples, we'll get a contrast. Third signal is the X-ray characteristics, which is coming from the deep of from the sample. This X-ray characteristic will give us the EDAX. That is it will tell us about the elements present in the samples. So we can quantify the elements present in the samples from boron to uranium. So any elements can be detected with the help of this X-ray characteristics. And the detector used for this is the EDS, that is energy dispersive spectroscopy. So let's see the secondary electron, that is the inelastic scattering. So specimen electrons are the secondary electrons, as I told earlier. So the energy transferred to the tightly bound inner shell electrons and the loosely bound outer shell electrons of the specimen. So the loosely bound outer shell electrons are removed from the specimen and they travels towards the electrons and gives us the secondary electron image. And the amount of energy transfers from beam electron to secondary is 25 to 30 electron volt. This secondary electron forms the secondary electron image. Backscattered electrons, those are the elastic electrons which are coming back from the surface of the electrons, the same electron beam which is hitting the samples, and those electrons are scattered back and gives us the contrast image. So the kinetic energy of those electrons remains unchanged, and less than 1 electron volt of energy is lost, and electrons are scattered by Coulombic interaction. The factor that affect the depth penetration. So when the electron beam touches the samples, so depth of penetration depends on the oscillating voltage that we are using, the atomic weight of the samples, that is the nature of the samples, whether it is metallic or non-metallic, and the angle of incidence of the beam. So these three things will decide the depth of the penetration, how much the beam will penetrate into the sample. So detector that we are using in SEM is the ED detector, which is used in high vacuum mode. So in SEM, normally we have a 3 mode of operations, that is a high vacuum, low vacuum, and ESEM, that is environmental scanning electron microscope. So generally it is also called a variable pressure mode. But in FA system, we have the 3 mode, that is high vacuum, low vacuum, and environmental mode. So in high vacuum, the ETD detector and VSE detector are active, whereas in low vacuum mode, LFD detector and VSE detector are active, and in ESE mode, the gaseous secondary electron detector is active. So depending on which mode we are selecting, the detector get activated. We also have a CCD camera inside the chamber, and for elemental analysis, EDS detector is used. The mode of operation, as I told you, the 3 mode of operation, that is high vacuum mode, low vacuum, and ESE. In high vacuum mode, the conductive samples are analyzed, and detector uses ETD and VSD. The non-conductive samples cannot be analyzed in high vacuum mode, because as we try to analyze those samples, they get charged up. So to analyze those type of samples, so we have to coat the samples with gold or platinum or silver. So coating is required for such sample which are not conductive to analyze in high vacuum mode. This is the image taken in high vacuum mode using the ETD detector, showing the metal surface, the roughness of the metal surface. This image is taken at 2000x magnification. Another image, that is a sample showing the cracks on the metal surface. This is the metal sample surface, but taken in this is the BSD image, backscattered image, showing the contrast. So elemental phase contrast. The higher the atomic number, brighter will be the phase. Lighter atomic number will give us the darker phase. So you can see the dark and bright phases in this image. This is called as a backscattered image. In low vacuum, non-conductive sample can be analyzed without coating. So coating is not required for non-conductive samples, because in low vacuum, we can adjust the pressure there, and the pressure range is from 10 pascals to 130 pascals. So depending on the nature of samples, how soft the sample is, we select the pressure. So that means there is not much vacuum inside the chamber. The vacuum is a little bit poor. That is a maximum up to 130 pascal we can set. So with this pressure, we can analyze the non-conductive samples without any preparation or without any coating, making it conductive. You can see the images captured in low vacuum mode using the detector LFD, and magnification is 1000x. So you can see the pollen grain image of an pollen grain. This is the backscattered image taken in low vacuum mode. Image of a pellet capsule, the cross section of the pellet, and you can clearly see the different layers of a pellets. This is another example for ESEM mode. The image is taken in ESEM mode by using the GSA detector. That is a fish mean the sperms of a fish. The image is taken at 6000x by using the pressure of 400 pascals. This is the feelers of a fly. Again, this image is taken in low vacuum mode. These are some example of images taken in GSD mode. So GSD, by using the GSD detector. So GSD detector is used in ESM mode. So ESM mode has a pressure range from 10 pascals to 2700 pascals. So we can adjust the pressure range from say 10 to 2000, any pressure depending on the nature of samples. Even we can adjust the temperature, humidity in environmental mode. So any type of samples which required a temperature say 0 degree or minus 10 degree, minus 5 degree, can adjust that temperature. We can set the pressure say 900 pascals or 500 pascals. So depending on nature of samples, even a soft sample can be analyzed in environmental mode. So this is our contact details. Thank you. Any questions?
Sir, I have one question.
Yeah.
I have one question.
Yes, sir.
Yeah, so you have very nicely given the details of SEM.
Yes.
And it is quite interesting because and quite important because many of the students
yes
join the conference and they should know the basics about this a very important technique. My question is regarding the advancement in the upcoming SEMs. So
Yes.
what we see is previously we have this electron gun thermionic, but
Yes.
then afterwards we come up with the field emission gun, electron gun. So likewise, what are the recent ongoing research is going on in SEM?
Sorry, can you come again, sir? I just putting the mic here.
Okay. So
Yeah,
my question is regarding what are the advanced things which are going on in SEM, because now nowadays I see that there is a new word coming, STEM, scanning
Yeah.
transmission electron microscope. So can you give some light on it?
Sorry to say you, sir, I am not aware about the transmission, but in AC, I can talk about the ACM because that is not my topic. TM.
Okay. So
Yeah.
in SEM, what is the new things?
Yeah,
are
in
going on?
ACM we have a FEC system, that is a field emission gun, FEG we call. So which is at a higher resolution. We can go up to 3 lakh X magnification in FESEM. Earlier tungsten based ACM are used where the resolution is also very less and the magnification we can go is around say maximum 1.5 lakh X. But in FESEM we can go more than 3 lakh X magnification and the resolution is also very good as compared to the tungsten based ACM. So we can detect the, we can analyze the sample say up to nano level, like we can measure the particle size around 10 nanometer or 50 nanometer in FESEM as well. As we can very much closer to TEM, we can say by using this FESEM.
Okay, sir. And I also come to know about 3D SEM. So what is can you?
3D SEM, no, I am not aware of that.
Okay.
Sorry.
Okay.
Yeah.
No problems. Okay.
Yeah.
Datta sir.
Yes. Bhaskar sir.
Yes.
Yes.
Yeah. Any questions? One question is there a difference between BioSEM and APSEM, ESM in terms of working principle? You might have seen the chat box.
No, sir. Just a minute. Okay.
There are two questions.
Two questions are there. Difference between a BioSEM and ESM in terms of working principle. Yeah, BioSEM is the same where the biological samples are done, but there is no such difference. Actually, there is no such bio or ESM. SEM is the instrument, that is scanning electron microscope, and ESM is the mode which is used in SEM. So in SEM, we have different 3 types of mode, that is high vacuum, low vacuum, and ESM. So ESM is not as such different SEM. It is a mode of operation in SEM itself. So in high vacuum, earlier only high vacuum instruments are available. So when we try to analyze the non-conductive samples or any biological samples in high vacuum mode, so it was not possible to analyze those samples in high vacuum mode. So we conduct those samples by using the gold sputtering, by making it conductive. But now the more advanced instruments are there with some low vacuum mode and ESM, that is environmental scanning electron microscope, that is the mode of operation. So in low vacuum mode, we can analyze the non-conductive samples but solid in nature. Whereas if the sample are more soft or any liquid sample, biological like bacteria, so there we use the ESM mode. So in SEM, we have these 3 different mode of operation. Yeah. Yeah. The next question is the lifespan of tungsten.
आपण आता ते मागे चालू झालंय का काहीतरी परत तसं एखादं वर्कशॉप घेऊया करू ना आपण
Lifespan of tungsten usually in SEM as a tungsten basically has a weak lifespan.
Right. The lifespan of tungsten is around say 90 to 100 hours, depending on the what voltage you are using regularly an hour. So on an average, the lifespan is 100 hours, you can say. And it is very cheap also, easily available, this tungsten filament as compared to FEC. Yeah. Any other question?
Now you have explained the microscopy from the fundamentals to the applied advances in this area, especially special attention towards the environmental scanning, electron microscope, EDX, and all these things. Okay, thank you very much for your valuable time spared for
sir.
this for this
Yeah.
workshop. Okay, thank you.
Yeah, thank you, sir.
Thank you on behalf of organizing committee.
Yeah. Welcome, sir. Yeah, thank you very much, sir.
Thank you. So next speaker for this session is Pramod Hande. Is actually the Master in Marketing Management, SIMSR, Mumbai University, Bachelor from Physics, RJ College, Mumbai University, and his working experience in, especially in currently working with Icon Analytical as a manager, sales and product support from 2019 to now. Working in optical microscopy since 2009, almost around 14 years experience is having in this area. Is going to talk on optical microscope for the material characterization. So welcome Dr. Hande for this session.
Thank you very much. Yeah, thank you very much for giving me an opportunity to speak here on optical microscopy. Would like to present further with the beautiful audience. So maybe start now.
Yes, sir. You start.
Yeah. I hope you can see my screen, sir.
Yes, we can see. Yes.
Myself, Pramod Hande, I am working with Icon Analytical, and we are going to talk about optical microscopy for material characterizations and the optical microscopy, how it is, what are the contrasting methods, and etc. So as Icon, we maintain the market leadership in the field of analytical instruments. We provide a better quality, on-time delivery, after-sales service to the customers. A company review, we are in the markets in 1996. We are ISO certified company, and we do have branch offices at Delhi, Kolkata, Bangalore, Chennai, Hyderabad, and headquartered in Mumbai. We do have different teams of sales, service, product supports, and we do have a senior sales and service management team of average experience of 25 years. So a team with the better knowledge and expertise. We are in the specializes in the field of analytical instrument, focusing on the microscopy, surface chemistry, preclinical imaging in biology sector, sample preparation, electron microscopy, consumables, laboratory, and also the Icon lab with the electron microscope in-house lab available for sample analysis. We're headquartered in Mumbai, so our lab is also at the same place. We do have 500+ installations in India, all over the product range what we cater to. We are catering premium institutes like IISER, IITs, major universities, research institutions, industries, R&Ds, pharma, all the sectors. And we represent these brands: Park Systems, Leica, Physical Electronics for AFM, optical microscopy, XPS, Emina KLA, that is surface analysis, cigarette Teledyne molecules, Lumix, spectral imaging. These are biological instruments related to. Now talking about optical microscopy. So my colleague Kiran already talked about scanning electron microscope and elemental mapping. We are going to talk about the optical microscopy, where you can't achieve the resolution like SEM, but it has some different positive applications and limitations we will talk about. So basic knowledge on fundamentals of optical microscopy. What I'm going to cover is some history, a short view on the past, finite, infinite optics, incident light beam path, as we are talking about the material characterization, some physics into it, the numerical aperture and the resolution, how it correlates and how it affect on a better imaging on optical microscopy, the objectives, which is heart of the system, and the contrasting methods, which will give you different aspects of the imaging. So what is microscope? Microscope, by definition, a piece of equipment that makes very small subject look big for you to able to see them with your eyes with the help of microscope. So it's a laboratory instrument used to examine the objects which are too tiny, too small, and microscope help you to invisible to the eye unless aided by the microscope. So this is an old picture where Gandhiji uses microscope. It is logo of one of the institute also in India. So as past 1665, Mr. Hooke, who used the microscope and visualized the microorganism first time. So some history on optics, the optics of the objective or lenses getting used in the microscope. So since 1665, until 1975, it was very conventional single monocular microscope with very basic things with the microscopy. 1975 metalloplan, like the microscope came with a better optics, which is which gives some added advantage to the microscopy with the reflected light for the samples which are opaque, which are non-transparent sample. Before that, it was always be seen with the only transmitted light samples where light passes through the sample. So these were the developments since 1975, then 1984, 89, 95, and 96 now. Since 96, this harmonic component system, it is a part of lens again. So throughout this RL optics, 250 mm, RFL optics, universal optics, delta optics, these were the advancement in the optics, and now HCS system, what we used in microscopy globally. Incident light beam path. So this is the basic design of the optical microscope in reflected microscopy, along with the polarization with contrasting methods. So how it works. Yeah, I hope you can see the pointer now. So this is the optical design incident light beam path for the microscopy. So this is the tube lens, the beam splitter to split the light which is coming from the source. So light will come from the source. With the beam splitter, it will reflect to the sample. The sample is here, the object is here. In between polarizer, Wollaston prism, these are the components in the light path. So light will fall on the sample, reflects back, and from the same beam splitter, it will go ahead, and with the from the tube lens it passes, and you can view it here with the eyepiece or camera as a digital imaging. In between, you can see this polarizer analyzer for reflected light, and polarizer again used as an objective as a polarizer here, as there is no transmitted light, only reflected light. So light will pass through this way and reflects back through this way. This is the simple incident light beam path without much contrasting methods. How the beam path goes in upright microscope and inverted microscope. So this is an upright microscope where in transmitted light, the light will come from this way, from the base. It will go through condenser. Condenser will condense the light, fall on the sample. Through objective, you can visualize through eyepiece or by camera, which is situated here. This is biological microscopy for transmitted light samples, or the samples which are transmitted in late nature, although it is from the material science. And this is the reflected light where the samples are opaque, which are non-transparent, semi-transparent sometimes, or translucent also. So light will come from here. This is the beam splitter which I talked to you about. The light will fall on the sample, reflects back, and you can see the image in eyepieces or camera. This is the simple path for upright microscope. Now for inverted microscope, it is inversely proportional to the upright microscope. The transmitted light will come from the top. So this is the transmitted light in case of inverted microscope. The light will fall on the sample through this condenser, and by this way you can image it here in eyepieces, or the camera can be situated here or at the base. I mean, there are multi positions available in inverted microscope. And in case of reflected light, inverted microscope has a reflected light at the base. The light will come from this way, fall on the object of the sample, reflects back, and you can see the image over here in eyepiece or the camera which is nearby the eyepiece. So these are the two things. Now upright and inverted has its own benefits and limitations. The limitation in terms of working distance in case of upright microscope, weight or size in case of upright microscope. Inverted microscope has an upper hand in that. So you can have a bigger size sample, you can have a height. In case of material science microscope like this, you can put a bigger sample in the height or in the weight or in the size. It is possible. Up to 3 kg is possible even. So yeah, these are the parts of upright and inverted. Now coming back to the heart of the system, that is objective and numerical aperture. So numerical aperture is the how to define numerical aperture is like objective determines the resolution of the details on depth of focus or contrast. So what is resolution is like once you can say there are two objects which you can differentiate, that means the resolution. Your resolving power is indicating that there are two objects sit beside. So if the microscope has a resolution of 1 micron, that means within a 1 micron area, you can define that there are two objects available there. That is the resolution. And this resolution will give you, microscope will give you a resolution because of the numerical aperture of the objective. So the formula is A is equal to N into sine U. U is this angle. So better the angle, better will be the resolution. So wider the angle, if the angle is wider, the capacity of taking light will be higher or greater, and that is how the resolving power is greater in the microscope. So higher the Na, lower will be the working distance, shorter the working distance. So higher the Na, higher the magnification will give you a better resolution, but working distance will be lesser, field of view will be lesser. The field of the sample which you are viewing will be lesser. Objective. So every objective generally gives you information about that objective. So for example, this is PL apo 40x into 40x oblique 0.85 correction. So PL apo defines the class of the objective. This 40 defines the magnification of the objective, and 0.85 defines the numerical aperture of the objective. And further corrected objective is defining further characteristic of the objective. The color coding, there will be color on the objective which defines the magnification again, or the light, the optimum light for the microscopy is getting defined by this color. You can adjust the condenser according to the objective color when you're doing imaging. So to get the optimum light towards the sample. So the colors would be red, yellow, green, blue, deep blue and white respect to the objective of 5x, 10x, 20x, 50x, 100x, 63x and 100x. Now, objective classifications. So basically, objectives are getting classified with the application or the kind of microscopy we want to do. Incident light microscopy, that is purely based in industry, where material or metallic sample or opaque samples are there. Then transmitted light, that is biology. So we have an objective corrected with the cover glass correction. As in, you generally cover slip your sample in case of biology. You fix the sample with the cover slip. In incident light or industrial scenario, that won't be there. Like you generally prepare a mold and then put your sample as in metal or rock or whatever in the mold, and then you observe with the microscope. Then correction. So there are objectives which are corrected for many aberrations and true color reproduction. So there are the classes of objectives which we have seen. Along with that, these objectives are corrected for further corrections in numerical aperture also. The observation methods, so there are different observation or contrasting methods which we are going to see further. So bright field, dark field, polarization, DIC, oblique illumination. These are the different contrasting techniques. Immersion, so there are different immersions available. There are dry objectives which we generally use it in industry. Apart from that dry, there are some oil objectives are also there, and further dispersions or oil immersions objectives are also there. Some water immersion objectives are there. So these are the different class of objectives further. The range in wavelength, so visible range of wavelength is 400 to 800 nanometer, but some objectives are also UV corrected or IR corrected respectively. So there are different types of objectives, different grades of objectives available. In case of contrasting methods, so bright field, dark field, pole, phase, these are the contrasting methods we have seen. So this is the simple diagram of bright field, where this is the light source. The light is coming from the source, beam splitter fall on the sample, goes up, and in eyepiece you can see the object. There is no another lens is available in between. There is only a beam splitter which is splitting the beam into two parts. Further is dark field. Now, what is dark field? If you can see this image, basically sometimes you cannot see the outlines in the bus. Or if you have a metallic sample and you want to see some cracks or some hollow marks on the topography of the metal, with normal microscopy you really cannot understand that there is a pore or there is a crack or how it is. You can just see the line. But with the dark field microscopy, you actually can see that depth on the surface of the sample, or crack in the surface of the sample. How deep that crack is, that also you can try to analyze. May not be, you may not find out the depth in that case because this is not a 3D microscopy, but this is 3D, pseudo 3D microscopy. So in this, what happened is, like, some mirrors will be there inside the toroidal mirror ring, and elliptical mirror would be there in the light path, and because of that the dark field microscopy is getting done or executed. The another contrasting technique is differential interference contrast. I have not taken the image of the microscope or path of the microscope in this case, just showing the images to you. The difference of images you can see. So this is DIC image. So there is a pore and we can see that there is some depth. We cannot measure the depth for sure, but we can see that surface and this portion has a different height. And the same way here, this is the bright field microscope image and this is the DIC image, where you can see some uneven waves are there on the sample, where here the image is very flat. So it's a 3D effect which is variable by shifting DIC Wollaston prism, and it does not correspond to the real surface topography. So it cannot give you a height, but it can show you that there is some height. This is another difference in the image. Like here you can see the bright field image very flat, you can't understand the heights, but here you can actually understand some depth is there in DIC image. Now there are different techniques, different contrasting methods. You can see bright field image, oblique image with some 3D. You can understand there is a depth. This is the dark field microscopy which I was talking about. So if there is a hollow portion, it makes black to white, white to black in simple language, in layman language. So it will change its color so that you can understand which are so if you can see these hollow white spots, you cannot see it in here in bright field microscopy, which is possible with dark field. So if there are pores, you can see the pores clearly. This is the polarized image. This is with etching sample lambda plates, so that you can see a different nice colors. And this is DIC. You can understand the difference between the height and surface of the sample, the topography of the sample with the 3D pseudo imaging. A few examples on optical microscopy. The images have been taken on material science samples. Now here I cannot relate every sample, but this is something related to glass, and this is some automobile part with the deposit. Few sample images from earth science, geology, and mineralogy taken on material science microscope. Sorry, polarizing microscope. I'm sorry, polarizing microscope, because polarizing microscope is getting used mostly in geology and material and mineralogy applications in geology labs, earth science labs. These are a few another images on the polarizing microscopy only. These three are asbestos images. This is coal image. This is also a coal image in between. This is polymer image. This is glass, and these two are from cement concrete, cement sample. These are few images from forensic science department, as in forensic science to investigate the crime. People uses microscope, and the samples can be fabric, thread, blood, and many more, sometimes even bullets with comparison microscope. For that also we have a solution. These are some biological images. Coming back to the metallography lab, so different metallurgical samples and with the different applications. I mean, there are multiple softwares to analyze your sample with the different ways. So we can understand the different phases up to around 10 phases at a time. If your sample have availability of those 10 phases, it is possible. The grain boundaries with the etching or non-etching sample to understand the grain size in your sample, so that you can understand the bond between two different particles, and you so that you can analyze how how your product is having a better strength. And there are multiple methods with another contrasting. So you can see a porocytes with 100x magnification, which can go up to 1000x, and also up to 2500x magnification in optical microscopy, which is possible nowadays. So coming back to applications, so where the microscope is getting used in material characterization. So there are different industries available where steel, cast iron, light metal, ferrous, non-ferrous metals, metal alloys. So here raw material, right from raw material to the final product, every R&D or quality control, you need an optical microscope to understand the strength of the product, or stiffness of the product, or surface of the product, or different qualities of the product. So microscope, optical microscope is very well getting used with the very different techniques, bright field, dark field, DIC pole, oblique illumination to understand the grain, graphite, surface analysis, everything. Going further into materials, so metal alloys, as we have seen previously, ceramics, compound materials, concrete, plastic, minerals, polymers. So these are also the different applications where optical microscope is getting used. Dark field, it's really rarely getting used, but polarizing microscopy is mainly used in plastic, minerals, metals, and ceramics, with the definitely DIC contrast. The another MEMS, the example where switches, medium PCBs, bigger PCBs, microsensors, these are the applications. Further, polymers and composites, so tire industry, fibers, injection molded plastics, carbon fibers. In fact, the paint industry, pigment, there also it is getting heavily used. Further to that, the raw materials, paper, cellulose, oil and gas industry, clay minerals, paper, wood, plastic, everything. I mean, from, as I said, raw material to final product, in between, there are multiple phases where microscopy is in use. So these are about optical microscopy. I tried to cover the application, different ways, segments for optical microscope, contrast technique of optical microscope, what I use available in microscopy field. I didn't cover stereo microscope as a small topic, important topic, but then I couldn't differentiate it well. So yeah, that's it from my end. Any questions?
Yeah, session is open for question. Yes, those who have question, they can raise their hand or they can simply type in the chat box. I think Pramod, there is no question, and thank you very much for your nice talk. And we have here with our session chair, Dr. Niranjan Ramgir. Pramod, maybe you can hold for a few minutes. Huh?
Thank you very much. I'll stop the screen.
Yes, okay. Niranjan, can you hear me? Hello? Niranjan, can you hear me? I think he has just...
Hello?
Niranjan, can you hear me?
Yeah.
Hello.
Sir, he's in the meeting, so might be he's in the meeting.
Okay. Can you make him a host? Mumin sir, can you make him a host?
Niranjan sir, please try to unmute yourself. You are the co-host now.
Yeah, I can hear you.
Okay. I think just last lecture is over. And last lecture was Mr. Pramod Thande from Microanalytical. And he has just concluded his talk. Please, you can give your remarks and comments.
Sir, it was a very nice presentation, sir. Thank you, Pramod, sir. It was wonderful. I was not known to much of these microscope levels and all, especially, we are from the undergraduate level. We are not exposed to all those things. It was wonderful, sir. Thank you very much, Pramod, sir. And the organizers, I am very much thankful for providing such a very good seminar, sir. Thank you, sir.
Yeah, thank you.
Thank you. Thank you, Krishna.
So myself Pratiksha Savak, and I am a SY BSc student, and I'm really thankful of Amita University that they conducted this program related to the knowledge of nanomaterial science. As I'm an undergraduate student, the concern of me for knowing about nanomaterial or the development happening in the nanomaterial sector was very less. So we are really thankful of all the professors who have given their time and let us know about the nanoscience. First of all, I would like to thank Professor Pavan Kumar sir, because they told us about the temperature dependence property and superplasticity and the strengthening in CONICRFEMN, which also known as Pavitra element, which is high entropy alloy using atomic stimulation, due to which we come to know about that high entropy alloys can also be used as a nanomaterial, and the reaction can, and whatever the mechanism was there, we came to know about it. We are also thankful. I'm also thankful to Dr. Sandeep Shinde sir that they told about the fluorine and molybdenum oxide, which can be used as a nanomaterial for different reactions. And also thankful to them that they told us that yet there is a scope of development in aromatic ring structure and new combinations can be tried. So the student, BSc students and MSc students can also work on it and can develop something on our own. We are also thankful of Shivraj Karver sir. They told us a lot about the thin film deposition, the preparation of the flame, and the main content, which was potential energy surface MEAD deposition stimulation process. We are really thankful of them. We are thankful of Dr. Kirti Rathi ma'am, that they told us about the sensors, different chemical sensors, electrophilic, hydrochloric in natures, and biological use of the sensor. What is how the sensors are being developed, and the basic knowledge which is unable for us to gather in such a small age has been given by ma'am. And we are also thankful of Dr. Krishna Pawar sir, who told us about the sensors which are now going to be used after few years, means the progress has been happening, and e-sensors that can be used, or the chemical sensors, whatever the properties are being added so that these sensors can be well developed. What are the things we have to keep in our mind? And all the things were told to us by Krishna Pawar sir, so we are thankful of them also. And we are also thankful of Aniruddha Basu sir, who told us about the P-type doping method. And also in this type, not only just sir made sure that they were telling about their research work, but also told us about transistor from the basic, and due to which we came to know about all our basic concepts were clear, and we came to know about proper information about the dopant C60F48. We are really thankful of you, sir. And also thankful of Kiran Bodkar sir, who told us about the basic principle of scan electron microscope, due to which we come to know about that quantum 200 scan electron microscope, how has been its use, what is its electron beam value, or what is the whole process happening at industrial level and higher institute research level also. And Pramod Hande sir, also we are thankful of you that you told us about the optical microscopy, and very nice images were being showed to us, and we came to know about this microscope used very well, and also the development stage. encouraged from the basic. And here also thank you of Latte sir that in the meantime they told us about their 2D nano material study related to the graphene. Sir told us about how to prepare graphene in simple ways in lab technology, which we students can also do by using our knowledge in chemistry. And I'm really thankful of the whole MIT group, Dr. Vyas sir, Dr. Suhas Zogrekar sir, Dattatreya Latte sir, and the coordinator Arif Sheikh sir, and other professors who I have forgot to take the name. I'm thankful of everyone.
Yeah, thank you, Pratiksha, for your nice compliment. Now we are nearly at the end of the all the sessions. Before I close, I'd like to thank the session chair, Dr. Niranjan Ramgir from Bhabha Atomic Research Center, Mumbai, and Dr. Bhaskar Sathe from Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, for chairing the session, and especially for completing the session exactly on the time. Since yesterday we are having very tight schedule. Yesterday there was a postal presentation. We have received nearly 67 presentations, and we have also finalized the 3 category of winners. The winner are from PhD student category, first category. The second category is from faculty category, and we have one more category, that is the UG and PG students. So in UG, we have 3 winners and 1 runner-up, and in PhD student category, we have 3 winners and actually 4 winners. 1 is tie and 2 runner-up, and in faculty category, we have 3 winners. So winners poster presentation prizes will be announced shortly. Kindly hold for another 10-20 minutes so that we can announce all these things in a valedictory function. So I think there is a tea break now. We'll be joining, or you can hold the same meeting. We'll start the valedictory function shortly. Thank you. Good evening, sir.
Good evening, Dr.
Okay. Riddhi madam, over to you.
Okay, sir. Thank you, sir. So, welcome everyone to the valedictory function for the international workshop on recent trends in functional nanomaterials for technological applications. I request Dr. Arif Sheikh sir to welcome the guests for the valedictory function.
Thank you, Riddhi. Am I audible?
Yes, sir.
Thank you so much. So, good evening, sir. Good evening to all of you, respected dignitaries on the dais, Honorable Founder President, Dr. Ashok Chauhan, sir, Honorable Chancellor, Amity University, Mumbai, Dr. Asim Chauhan, sir, Honorable Vice Chancellor of Amity University, Mumbai, Professor Dr. A.W. Santosh Kumar, sir, and Honorable President, Amity University Science and Technology Innovation Foundation, Director General, Amity Doctorate of Science and Innovation, and Chancellor of Amity University, Chhattisgarh, Dr. A.W. Silvamurthy, sir, all distinguished speakers, participants from Icon Analytical Labs, Navi Mumbai, my faculty colleagues, and dear participants. On behalf of organizing committee, it is my pleasure to welcome you all to the valedictory function of the international workshop on recent trends in functional nanomaterials for technological applications, organized by Center of Nanoscience and Nanotechnology, Amity University, Mumbai. So basically, we are at the end of our program. We have started our program yesterday, where total 200 participants have registered, and out of which 70 participants have presented their poster, and we have come up with our examiners have come up with 3 best poster presentation in each category, which will be announced soon. So thank you, Riddhi ma'am. Over to Latte sir. Could we ask participant to share their experience?
Yeah, one or two participants you can ask.
Yeah, so on behalf of organizing committee, I request participants, if anyone want to share their experience in a couple of minutes, please quickly respond. Okay, so I think, sir, there is not no more friends, so we will continue with our program. Over to you, Latte sir.
Okay, Riddhi madam, now sir will give the address.
Yes, sir.
Can you
Yes, sir, yes.
request closing
Sir,
remarks by our
yes, sir.
honorable VC sir?
Thank you, Dr. Latte.
Thank you, sir.
So thank you very much for giving this opportunity on the closing note of International Conference on the recent trends in functional nanomaterial for technical applications. At the outset, I am really happy and thank convener Dr. Latte and co-convener Dr. Arif and all the advisory committee members, Dr. Riddhi, for making this a great success. Special thanks and applauses to all the 7 speakers, right, starting from Pawan of USA to Sandeep from Germany, Shivraj from Netherlands, and Kirti from Korea, and Krishna from Korea, and Anuradha from Saudi Arabia, and also Anand. For this valedictory, Dr. Asim Chawanji, our Honorable Chancellor and President, was supposed to attend, but we have an international delegate in Delhi currently, and they have a meeting now with the founder president. So he is quite tied up. So he has bestowed his blessings and wishes for this international conference. At the outset, it is a very short learning experience, but I should say that it's an accelerated experience from hearing from the learned people on the nanotechnology application part. And I think these 2 days of deliberation would be a great success and would have brought new knowledge, both on the arena of the students as well as the faculty members. And I also congratulate the award winners of their research presentations, student friends. And Amity University Center for Nanotechnology is known for its publication and good work. And I should really congratulate the Center for Nanotechnology for taking this effort. And I would also suggest this kind of a big event would want to go on an offline event at the AUM that will invite a lot of big people in the area to come and witness what is really happening. Thank you very much.
Thank you, sir, for your kind words and blessings. Latte sir, should we proceed with the prize presentations? Sir?
Yes.
Okay. So.
Yeah,
Okay.
Thank you, sir, for your all support, encouragement, and definitely will take your words. In December this year or max in January 2023 will be arranged physical event, which will be 3-day kind of thing where participants from not only from India, from abroad also will come physically. They will interact with our faculty and students. Thank you, sir. Thank you. Yes, Riddhi madam. You are please unmute.
Sorry, I'm extremely sorry. So next we have the most awaited movement for all those who have participated in the poster presentation. So the prizes for the poster presentation will be declared. I request Dr. Dattatraya Latte sir to declare the winners of the poster presentation.
Okay.
On the 3 categories.
Latte ji, I have another meeting, so let me just log off. All the best.
Yes, sir.
Thank you,
Thank
sir.
you. Thank you, sir.
Thank you very much.
Thank you so much.
Thank you, sir, for your all support, help, and blessing. Thank you, sir.
Thank you, sir.
Okay, we have three categories of winners of best poster presentation, undergraduate and postgraduate students. Then we have another category, winners of best poster presentation, PhD student category. We have third category of winners of best poster presentation, faculty category. So I'll announce first the best poster presentation winners, undergraduate and postgraduate students. Runner-up prize goes to, any guess? Runner-up prize goes to Mr. Amar Ali from International Islamic University, Islamabad, Pakistan. Topic was synthesis and frequency independent dielectric properties of undoped and amend code of NI nanoparticles. Congratulations, Mr. Amar Ali, for runner-up prize. Third prize of poster presentation undergraduate and postgraduate student category goes to Mr. Punit Kumar M. Srinivasappa from Center for Nano and Material Science, Jain University, Bangalore. Topic is solvent-free chemical transformation of carbon dioxide and oxaloethene over porous trimetallic oxide from catalyst. And the second prize goes to Mr. Aryan Modi from MIT University, Mumbai. The topic of presentation was cancer treatment BIT technology. Heartily congratulations to Mr. Aryan Modi on behalf of organizing committee. And first prize under the category of undergraduate and postgraduate goes to Mr. Rohit Raghunath Nikam, Center for Nano and Material Science, Jain University, Bangalore. My topic of presentation was robust silica nanotubes functionalized with base as an efficient and selective catalyst for sustainable fixation of carbon dioxide into value added product. Heartily congratulations to all the winners under this undergraduate and postgraduate student poster prize. We'll issue online certificate of this winner shortly. Once again, congratulations to all the winners under this undergraduate and postgraduate student category. Okay, I will announce now the winners of best poster presentation under PhD student category. This is most awaiting event for any PhD scholar during his or her tenure of the PhD. I will announce first the runner-up prizes. Runner-up first prize, second prize goes to, runner-up second prize goes to Ms. Alisha Lalhali from Punjab University. Topic of presentation was development of fluorescent nanotube-based biosensor for sensing of heavy metals. First runner-up prize goes to Mitheri Trimuvaram from National Forensic Science University, Gandhinagar. Topic of presentation was cytosine functionalized celluloid nanotubes as a receptive surface for glucose and copper to perform degradation of chlorophylls in aqueous environment. Okay, best three poster prizes under PhD student category. There are in third number, there are two type. Third prize goes to Mr. Deepak Devadika from CNMS Jain University, Bangalore. Topic of presentation was new pyridine-based conjugated system for reversible acid-based sensor. There is one more third prize, which goes to Ms. Smruti Raut from ICT Indian Oil Campus, Bhubaneswar. Topic of presentation was pharmaceutical novel solid forms of mineral with advanced psychochemical properties. Second prize goes to Ms. Namsiar K from Jain University, Bangalore. Topic of presentation was 2D black phosphorus polyurine hybrid for efficient supercapacitor and hydrogen revolution reaction application. And first prize goes to, any guess? First prize goes to, I will tell the topic, Amexin based all solid state supercapacitor with vertical graphene arrays as the current collector experiment and theoretical investigation by Mr. Abhinandan Patra from Center for Nano Material Science, Jain University, Bangalore. My heartiest congratulations to all the winners a poster presentation from PhD student category. Congratulations. Okay, the last winner, best poster presentation faculty category. There are 3 winners. Third prize goes to Mr. Amay Jayachandra More from Amity University, Maharashtra. His topic of presentation was high velocity impact resistant nanocomposite. Heartiest congratulations to Mr. Amay More for the award. Second prize goes to Ms. Gunchita Kaur Vadawa from Amity University, Maharashtra. Topic of presentation was boron nitride based polymer composite structural applications. Heartiest congratulations, Ms. Gunchita. And first prize goes to Dr. Sarup Roy from Shalini University. Topic of presentation was development of gelatin cellulose nanofiber based functional films induced with mushroom mediated sulfur nanoparticles for active packaging application. Thank you. Congratulations to all the winners of the poster presentation. And we shortly send you the e-certificates to all the winners, as well as we will also send the participation certificate. Those who have attended full day program, will send them the participation certificate as well. Okay, Riddhi madam, over to you.
Thank you, sir. So that were heartiest congratulations to all the winners of the poster presentations. And we all wish you all the best for your future research. And after the poster presentation, we would like to move to the vote of thanks for the complete workshop. I request Latte sir to give us the vote of thanks.
Okay. Okay. Thank you, Riddhi madam. Good evening, all gathered here on this wonderful day. It is an honor to offer a vote of thanks on the occasion of international workshop conducted by Center for Nanoscience and Nanotechnology, Amity University, Mumbai, on recent trends in functional nanomaterials for technological application 2022 by Amity University, Mumbai. First of all, I'd like to thank Amity Foundation for Science and Technology Innovation Alliance and Amity University, Maharashtra, Mumbai for supporting the today's event. I'd like to take this opportunity to thank Dr. William Silamurthy, sir, President of Amity Science and Technology Innovation Foundation and Director General for Amity Director of Science and Innovation. Sir, fellow of all the science academies of India. In fact, sir is extremely busy. Morning, he has given us some time for us. Thank you, sir, for your presence, guidance, valuable remarks, suggestions, and all support given to conduct this event. I extend my thanks to visionary leader, Dr. A.W. Santosh Kumar, Honorable Vice Chancellor, sir, Amity University, Maharashtra, Mumbai, who kindly agreed to host this particular workshop via online platform. Also, I'd like to thank our eminent speakers who agreed to deliver a talk, and happy to inform that our speakers were joined from USA, South Korea, Netherlands, Saudi Arabia in this particular workshop. Also, thanks all the session chairs for smooth conduction of this workshop. I also thank all the examiners for evaluation of the workshop. I'd like to thank Dr. Riddhi madam for anchoring this particular workshop in the morning as well as this time also. I extend my sincere thanks to all my colleagues and mentors from Noida and Mumbai campus for all support and freedom given to me to organize this particular very important workshop on nanomaterials and technological applications. I extend my gratitude to Honorable Professor Dr. Ashim Chavan, sir, Chancellor, Amity Group of Universities, for encouragement and to motivate to achieve many more goals. Thank you, sir. I'd like to thank Amity University IT advisory team, especially for being with us since last 2 days. I'd like to thank media team and the representative for giving the due publicity for our webinar on various platforms. I'd like to thank all our PhD scholars from Center for our help support, especially Ms. Gunchita, Ms. Urmila, Umay More, Prashant ji, and Jitendra. I'd like to thank Icon Lab, Navi Mumbai for the financial support. I also like to thank Anton Power India Private Limited, Mumbai, for their involvement in this particular workshop. I would like to thank all the participants who connected via various campuses of Amity University located across the globe, as well as the all participants who has taken active part in this particular workshop in the form of poster presentation and in the form of audience. Without that, this program would not have been succeed. Once again, I thank you one and all wholeheartedly. Thank you. I also like to thank my colleague, Dr. Arif, for his all help and support. And I think with this, we declare that this particular workshop has been concluded. And now I over to Riddhi Madam. Thank you. Thank you.
Thank you everyone for your kind participation. Hope this workshop has been enlightening to you all. Thank you, Latte sir and Sheikh sir, for organizing this workshop. With the last vote of thanks from Latte sir, we declare.
Ma'am, we are completing session with the national anthem.
Sorry.
Okay, we'll play the national anthem.
Yes.
National anthem, and then the session will be over. Thank you, all the participants and everyone. Thank you.
Thank you.
Sir, not working.
नाही का?
नाही.
स्क्रीन शेअर करून स्क्रीन शेअर करा आणि प्ले करा. शेअर स्क्रीन आणि कुठे कुठली आहे गेम सर? असं करताय ना. बघा बघा. येते का?
Share with audience. So I think this is my Spanish, French, and so this is what is the concept of mind of that. You know, I think mind of that word is quite big. It's not very clear with the kids. This is the concept of mind of that. Of nature that is basically as